What if most of the universe is made up of something we cannot see or fully understand? Dark energy and dark matter, elusive forces that control the cosmos, remain among the greatest mysteries that challenge our understanding of reality. But within these forces lies objects, so unimaginably strange that scientists still don't know what they are. Join us as we delve into the biggest mysteries in the universe. Dark energy is a mysterious force that plays a crucial role in the expansion of the universe. To understand it, picture the universe as a balloon being inflated. As the balloon expands, sections of it move away from each other. Dark energy is thought to be the driving force behind this acceleration, pushing galaxies apart at an ever-increasing rate. The discovery of dark energy began in the late 1990s, when astronomers were studying supernovae, which are the explosive deaths of certain stars. These astronomers, studying light from these distant explosions, expected to see all galaxies slowing down as gravity pulled them together. However, they found something surprising. The further they looked, the faster those galaxies seemed to be moving away. This unexpected observation prompted scientists to propose the existence of dark energy. It was a radical idea, suggesting that not only did space itself expand, but it was doing so at an accelerated pace due to this unseen force. Since then, dark energy has become a fundamental component of modern cosmological theories, although its exact nature remains one of the great mysteries in science today. Dark energy and dark matter are two mysterious components of our universe, but they serve very different roles. Dark matter acts like an invisible glue, holding galaxies and galaxy clusters together. Imagine trying to keep a group of stars in a friendship circle. Dark matter provides the gravitational pull that prevents these stars from drifting apart, even though we can't see it directly. Scientists have observed its effects by measuring the way light bends around massive objects and tracking the movements of galaxies, which indicates that there's more mass present than we can observe. On the other hand, dark energy is a force working against gravity. Think of it as an unseen hand pushing galaxies apart, contributing to the universe's rapid expansion. While we perceive this expansion as galaxies moving away from each other, dark energy continues to gain importance over time, influencing the cosmos on a much larger scale. It's as if the universe is filled with a repulsive power, causing it to stretch and expand, almost like a balloon inflating. In short, dark matter pulls things together, creating structure in the universe, while dark energy pushes things apart, driving the expansion. Understanding these two elements is crucial for grasping how our universe functions and evolves. Each plays a unique and vital role in shaping the cosmos as we know it. Dark energy plays a crucial role in the way our universe is expanding. To understand its influence, visualize the universe as a stretching balloon. As the balloon inflates, the surface expands, and this illustrates how galaxies are moving away from each other. Initially, it might seem that gravity, the attractive force between masses, would slow down this expansion. However, dark energy acts like a repulsive force that accelerates this process. Imagine that as the universe expands, dark energy fills the space. Its properties push against the pull of gravity, leading to a situation where the expansion doesn't just continue, it speeds up over time. This means that not only is the universe getting larger, but it is doing so at an increasing pace. The more we learn about dark energy, the more we realize how mysterious it is. It makes up a significant portion of the universe, yet we cannot directly observe or measure it. Scientists have inferred its presence through observations of distant supernovae and the large-scale structure of the universe, which show that distant galaxies are moving away from us faster than we would expect based solely on gravity. As researchers explore this cosmic phenomenon, they are faced with many questions. Why is dark energy causing this rapid expansion? How does it interact with the other forms of matter and energy in the universe? Each discovery leads to a deeper understanding of the universe itself, shaping our view of its past, present, and future. The dance between dark energy and the cosmos continues to be one of the most exciting frontiers of modern astrophysics. Dark energy is one of the most intriguing mysteries of the universe. It makes up a significant portion of all energy in the cosmos, and its exact nature remains elusive. One of the leading theories proposes that dark energy is a property of space itself. As the universe expands, new space comes into existence, and this space could have an energy density that exerts a repulsive force, pushing objects apart. Another theory is linked to the idea of a constant force, often referred to as a cosmological constant. This concept suggests that dark energy has a uniform energy density filling space evenly, regardless of the expansion of the universe. Think of it like a balloon that inflates. No matter how big the balloon grows, the surface tension feels the same throughout, suggesting that dark energy continues to act consistently as the universe expands. There are also theories related to dynamic fields, known as quintessence. This idea posits that dark energy is not constant, but rather a field that changes over time. Just like the weather can shift, so too could the characteristics of dark energy, influencing how quickly the universe expands at different points in its history. Lastly, some researchers are probing the possibility of modifications to our current understanding of gravity. In this scenario, dark energy might emerge from alterations in gravitational laws on cosmological scales. Essentially, this means that what we perceive as dark energy could be the result of gravity behaving differently when looking at the universe as a whole. As scientists gather more data, these theories continue to be refined, paving the way for a deeper understanding of the enigmatic force driving the universe's accelerated expansion. Each theory presents unique implications for the future of the cosmos, and ongoing research may eventually unravel the true nature of dark energy. Scientists measure the effects of dark energy on cosmic structures by observing how galaxies and clusters of galaxies behave over time. Dark energy is a mysterious force that is thought to be driving the accelerated expansion of the universe. To understand its influence, researchers look at the large-scale structure of the cosmos, how galaxies are distributed and how they move apart. One fundamental approach involves studying distant galaxies. As light from these galaxies travels towards us, it carries information about their existence billions of years ago. By comparing the positions and brightness of these distant galaxies to those that are nearer, scientists can determine how the expansion of the universe has changed over time. They also measure the light from supernovae, which are exploding stars. These supernovae can serve as standard candles because they have a known brightness. By examining how bright these explosions appear from Earth, researchers can calculate their distance. When they analyze these distances in conjunction with redshift, the shift of light to longer, less energetic wavelengths due to the expansion of space, they can infer how quickly the universe is expanding and how dark energy influences this rate. Additionally, scientists utilize gravitational lensing, where massive objects like galaxy clusters bend light from more distant objects. This bending reveals how much mass exists in those galaxy clusters and how the expansion of the universe affects the arrangement of matter. By studying the patterns of lensing, researchers can further probe the role of dark energy. All these methods combine to create a fuller picture of the cosmic environment. Each measurement helps build a clearer understanding of how dark energy impacts the universe's fate and its large-scale structures, guiding scientists in figuring out one of the cosmos's greatest mysteries. Dark energy is a mysterious force that plays a crucial role in shaping the future of our universe. Imagine the universe as a balloon being inflated. At first, the expansion of this balloon was slow, but as time went on, something unusual happened. The expansion started to speed up. This acceleration is attributed to dark energy. Dark energy acts like an invisible hand pushing galaxies apart, causing them to move away from each other at an increasing rate. Scientists believe that it makes up a significant portion of the universe, more than regular matter and energy combined. As we look into the far future, the effect of dark energy becomes even more pronounced. If this acceleration continues, galaxies will drift farther apart, and eventually distant galaxies may become invisible, as their light will take longer to reach us than the expansion of space. Over time, this could lead to a scenario often referred to as the Big Freeze. In this distant future, the universe could become a cold, dark, and empty place, with stars running out of fuel and galaxies disappearing from sight. Stars would burn out, leaving behind black holes or neutron stars, and the overall temperature of the universe would drop significantly. This outcome raises profound questions about the ultimate fate of everything we see around us. Dark energy, therefore, is not just a scientific curiosity. It is a central player in the story of the universe's evolution, influencing its vast future in ways we are only beginning to understand. The study of distant supernovae is a key tool for scientists trying to unravel the mystery of dark energy, the force believed to be driving the accelerated expansion of the universe. Supernovae are explosive events marking the end of a star's life. Among them, a specific type called Type Ia supernovae is particularly valuable. These explosions occur in binary star systems, where one star siphons material from its companion until it reaches a critical point and detonates. Because Type Ia supernovae have a consistent peak brightness, they act like cosmic beacons. By measuring how bright these supernovae appear from Earth, scientists can gauge how far away they are, similar to how a lighthouse's light can indicate its distance based on brightness. When astronomers observe distant supernovae, they find that these explosions are fainter than expected if the universe were simply slowing down or expanding steadily. Instead, their dimness suggests that the universe is expanding at an accelerating rate. This unexpected acceleration implies that something is pushing galaxies apart, which is where dark energy comes in. By mapping the light from numerous supernovae across time, scientists can create a detailed picture of the universe's expansion history. This research helps to confirm that dark energy constitutes a significant portion of the universe's total energy content, influencing its fate and structure. Ultimately, studying distant supernovae provides critical evidence about how our universe is changing, shedding light on one of the most profound mysteries in modern astrophysics. The cosmic microwave background, or CMB, serves as a crucial piece of the puzzle in understanding dark energy. Think of the CMB as the afterglow of the Big Bang, a faint radiation filling the universe that provides a snapshot of the cosmos when it was just a few 100,000 years old. By studying this ancient light, scientists can learn a lot about the universe's early conditions and its overall structure. When researchers measure the CMB, they look at tiny temperature fluctuations across the sky. These fluctuations reflect the density variations in the early universe, which ultimately shaped how galaxies formed and evolved. By analyzing these patterns, scientists can determine the amount of ordinary matter, and dark energy that exists in the universe. Dark energy is the mysterious force driving the accelerated expansion of the universe. The CMB measurements help establish the universe's geometry and its overall density. If the universe's density is below a certain point, models suggest that it must be dominated by dark energy, which counteracts gravity and pushes everything apart. Thus, CMB research not only highlights the universe's history, but also provides essential data that informs theories about the nature of dark energy. The cosmic microwave background is not just a relic of the past, it's a tool that unlocks the mysteries of how our universe is expanding and the role that dark energy plays in that process. Dark energy poses one of the most significant puzzles in contemporary physics and cosmology. At its core, dark energy is an unknown force that makes up a large part of our universe, pushing galaxies apart at an accelerating rate. This phenomenon directly challenges our understanding of gravity. We typically think of gravity as a force that attracts objects, pulling them closer together. However, dark energy appears to work in the opposite manner, driving them apart. The existence of dark energy forces scientists to reconsider their theories about the universe's composition and evolution. Traditional ideas suggested that gravity should slow the expansion of the universe by pulling galaxies towards each other. The observed acceleration of this expansion indicates that something fundamental is missing in those theories. Furthermore, the nature of dark energy remains elusive. It does not fit neatly into the categories of matter or energy we know about. While we can detect its effects through the movement of galaxies, we have yet to identify what it actually is. This unknown factor leads to ongoing debates and research, pushing scientists to explore new models and ideas, such as the possibility that our understanding of gravity itself may need revision. Some physicists are even investigating the idea that dark energy might be a property of space itself, rather than a form of matter. This challenges the very fabric of how we conceptualize the universe. As researchers uncover more about dark energy, they may need to rethink not only the makeup of the cosmos, but also the fundamental laws of physics as we know them. Each discovery pushes the boundaries of our understanding, urging us to explore further into the mysteries of the universe. Exploring dark energy presents us with a range of technological challenges that researchers must overcome to deepen our understanding of this mysterious force. Dark energy is believed to make up a significant portion of the universe. Dark energy is believed to make up a significant portion of the universe, but remains largely invisible and undetectable with current tools. One major challenge lies in the sensitivity of our instruments. Detecting the subtle effects of dark energy requires advanced telescopes and detectors that can measure minute changes in the universe's expansion rate and its structure over vast distances. Another hurdle is the sheer scale of the observations needed. The universe is vast beyond imagination, and gathering enough data from a wide array of angles and distances requires powerful technology and significant time investment. Advanced satellites and space missions need to be developed to get above the atmospheric distortions that can interfere with our observations. Furthermore, data processing is a considerable challenge. The amount of information collected from observations is immense, and sifting through this data to find relevant patterns related to dark energy requires sophisticated algorithms and supercomputers. Lastly, there's the uncertainty factor. Dark energy acts in ways that are still not fully understood, meaning that creating experiments and missions is complex. Designing equipment that can adapt to unforeseen results or unexpected findings in our research is crucial. These technological challenges highlight the frontier of modern cosmology and the ongoing quest to unravel the secrets of the universe. Dark matter is a mysterious substance that makes up a significant part of the universe, yet it remains invisible to our current instruments. Imagine trying to understand a puzzle with many missing pieces. Dark matter addresses those gaps in our understanding of the cosmos. Though we cannot see it directly, scientists infer its presence through its effects on visible matter, such as galaxies and clusters in the universe. To comprehend why dark matter is fundamental, we can start with how galaxies form and move. When we observe galaxies, we see they are rotating at speeds that should send them flying apart if only regular matter were present. However, they stay together, suggesting something unseen is exerting additional gravitational pull. This unseen force is attributed to dark matter. In simple terms, think of it as the scaffolding that holds galaxies together, allowing them to evolve and give rise to the complex structures we see today. Furthermore, dark matter plays a crucial role in the overall shape and expansion of the universe. During the early moments after the Big Bang, dark matter helped pull matter together, leading to the formation of galaxies and galaxy clusters. Without this gravitational influence, the universe we know would look vastly different. The existence of dark matter, then, is integral to understanding how cosmic structures came to be and continue to evolve. As researchers delve deeper into this elusive material, they are piecing together the workings of the universe, revealing a deeper story about its origin, structure, and destiny. This ongoing investigation stands as a testament to our quest to understand not just what is visible, but the profound mysteries that lie beyond our sight. The story of dark matter begins in the early decades of the 20th century, when astronomers began to notice something strange in the movements of galaxies. They expected to see a certain pattern in how these galaxies rotated, influenced by their visible mass like stars and gas. However, they found that some galaxies spun much faster than they should if only visible matter were taken into account. This discrepancy prompted scientists to wonder if there was something else at play, something they could not see. To understand this, consider a carousel. As the horse moves closer to the edge, it spins faster. If you were watching from a distance and only counted the visible horses, you would assume they were balanced perfectly. But if you noticed that they were moving far too quickly for the number of horses you could see, you might suspect an invisible force was at work, pulling them along. The term dark matter was introduced in the 1930s when an astronomer named Fritz Zwicky studied galaxy clusters. He observed that the mass of visible galaxies in the clusters was not enough to account for the gravitational pull needed to hold them together. His findings suggested that there was a significant amount of invisible mass, which he called dunkle materie, or dark matter. Yet, dark matter remained elusive. It was only through subsequent research that further evidence piled up. For example, studies of cosmic microwave background radiation, an afterglow from the Big Bang, revealed subtle patterns that provided clues about the universe's composition. Today, scientists estimate that dark matter constitutes a large portion of the universe, though it neither emits nor absorbs light, making it incredibly difficult to detect with conventional methods. Even in present times, we have yet to observe dark matter directly, but its presence can be inferred through its gravitational effects on visible matter. For instance, the way galaxies bend light from objects behind them. A phenomenon known as gravitational lensing provides strong indirect evidence of dark matter's existence. The quest to understand dark matter continues as researchers around the world work to unlock its many mysteries. Dark matter is a mysterious component of the universe, making up a large part of its total mass. Scientists are still trying to figure out what it really is, but there are several leading candidates for the particles that could make up dark matter. One of the main contenders is called a weakly interacting massive particle, often shortened to WIMP. Imagine a particle that is heavy enough to have a significant gravitational effect, but interacts very weakly with regular matter. This means it could pass through objects, including stars and planets, without any notice. WIMPs are appealing because they fit into existing theories of particle physics and might be detected through their rare interactions. Another potential candidate is an axion. Axions are hypothetical particles that are incredibly light and represent a theoretical solution to problems in particle physics. If they exist, they could form a type of dark matter known as cold dark matter, which behaves in a particular way to help explain how galaxies form and move. There are also sterile neutrinos, which are a heavier form of neutrinos that do not interact with regular matter in the same way that typical neutrinos do. They could provide the necessary mass and behavior to fit the models of dark matter. Finally, there are theories around modified gravity, which consider that the effects attributed to dark matter might actually stem from alterations to our understanding of gravity rather than the existence of unseen particles. This view suggests that the universe behaves differently at large scales than we think. While all these candidates are intriguing, researchers are actively conducting experiments to search for direct evidence. The search for dark matter particles continues to thrill scientists, as uncovering their identity could lead to a deeper understanding of the universe itself. Gravitational lensing is a fascinating phenomenon where massive objects like galaxies or clusters of galaxies bend the light from distant objects behind them. This bending occurs because of the strong gravitational fields created by the mass of the foreground object, much like how a glass lens focuses light. When scientists observe this effect, they can gather information about both the object causing the lensing and the background objects. As light travels towards us from a distant galaxy, if it passes near a massive galaxy cluster, that cluster's gravity warps the space around it. This warping causes the light to follow a curved path, which can lead to distorted or magnified images of the background galaxy. By studying these images, researchers can map the distribution of mass within the foreground cluster, including both visible stars and galaxies and the invisible dark matter. Dark matter does not emit, absorb, or reflect light, making it undetectable directly. However, its presence is inferred through its gravitational effects. Gravitational lensing gives us a crucial tool because the amount of bending depends on the total mass of the lensing object, including both visible matter and dark matter. By analyzing how light bends around these cosmic structures, scientists can estimate how much dark matter is present, even though we can't see it. This technique allows astronomers to create detailed maps of dark matter's distribution in the universe. It highlights the locations and structures of dark matter across vast distances, revealing that it does not clump together in a way that would mirror visible matter. Instead, it tends to take on a more diffuse, spread-out form. This has profound implications for our understanding of the universe, as it not only confirms the existence of dark matter, but also helps us understand how it interacts with visible matter, influencing galaxy formation and the large-scale structure of the cosmos. Dark matter is an invisible substance that plays a crucial role in shaping our universe, especially the formation and behavior of galaxies. Think of dark matter as the scaffolding that holds together the large structures we see in space. While ordinary matter, the stuff we can see, like stars, planets, and gas, can be thought of as the building blocks of a galaxy, dark matter provides the framework within which these building blocks gather and grow. When galaxies begin to form, they require a gravitational pull to attract ordinary matter. Here is where dark matter comes into play. It is present in vast amounts, and creates a significant gravitational influence. This allows gas and dust to clump together and start forming stars. Without dark matter, galaxies would not have the necessary mass to hold onto their gas and retain it long enough for stars to form efficiently. Additionally, dark matter affects how galaxies move and interact with one another. Imagine a galaxy moving through the universe like a boat on water. Its path is influenced not just by the visible waves, but also by the underwater currents, which represent the gravitational effects of dark matter. This hidden mass helps to determine the rotation speeds of galaxies, often making them spin faster than would be expected based solely on their visible content. Moreover, dark matter is believed to form large halos around galaxies, acting like an invisible cocoon. This halo slows down the escape of gas and dust, allowing conditions for star formation to last longer. However, these halos also play a role in gravitational interactions between galaxies. When two galaxies meet, the dark matter component can dictate how they merge or interact, often resulting in new structures or even triggering bursts of star formation. Dark matter is essential for the stability, structure, and evolution of galaxies. It sets the stage for their formation, influences how they interact with each other, and ensures that they maintain their integrity, shaping the cosmic landscape we observe today. Without dark matter, the universe would be a much different place, lacking the rich tapestry of galaxies that we see scattered across the night sky. Detecting dark matter directly is one of the most significant challenges in modern physics, as this mysterious substance makes up about 27% of the universe, yet does not emit light or energy that we can observe directly. Currently, there are several experiments meticulously designed to uncover the secrets of dark matter. One approach involves detecting weakly interacting massive particles, or WIMPs, which are a leading candidate for dark matter. Experiments such as the Large Hadron Collider have a role in exploring these particles when conditions recreate the high energies of the early universe. Meanwhile, underground laboratories, shielded from cosmic rays and other interference, host detectors like the Lux-Zeppelin experiment. These setups aim to capture the rare interactions between dark matter particles and normal matter, using sophisticated technologies that are extremely sensitive to the faintest signals. Another promising strategy utilizes cryogenic dark matter searches. These detectors cool materials to very low temperatures, making them less susceptible to noise from other particles. By observing minute energy changes when a dark matter particle collides with an atom in the detector, scientists hope to collect clear evidence of dark matter. Additionally, some researchers are exploring other types of theoretical particles, such as axions, which might account for dark matter. Experiments like the Axion dark matter experiment are set up to search for these particles by employing strong magnetic fields and highly sensitive equipment to detect any faint signals that these elusive particles may create. While these endeavors involve complex technology and innovative techniques, the heart of their efforts remains grounded in a fundamental curiosity about the universe. Each experiment provides pieces of a larger puzzle, as scientists strive to illuminate the shadows cast by dark matter and enhance our understanding of the cosmos. Dark matter plays a crucial role in shaping the universe's structure on a grand scale. Consider it as a hidden framework that influences how galaxies and clusters of galaxies form and organize themselves. Unlike ordinary matter, which makes up the stars, planets, and all visible objects, dark matter cannot be observed directly. Instead, we detect its presence through its gravitational effects. As the universe expanded after the Big Bang, tiny fluctuations in density helped form the first seeds of structure. Dark matter, which is much more abundant than ordinary matter, began to clump together under its own gravity. This clumping created a sort of scaffolding that helped gather regular matter, allowing galaxies to coalesce and grow. Imagine a net with large knots spaced throughout it. The knots represent areas of higher dark matter concentration. Ordinary matter is drawn toward these knots, creating galaxies in the process. This gravitational pull is what leads to the formation of vast cosmic structures, such as galaxy clusters and superclusters, which are essentially groups of galaxies bound together. Furthermore, the distribution of dark matter influences the movement of galaxies. Galaxies are not randomly scattered. Instead, they align along specific paths that reflect the underlying dark matter structure. This creates filaments and voids in the cosmic web, the vast network of galaxies throughout the universe. The areas where dark matter is denser are where we find more galaxies, while large empty spaces or voids occur where there is less. Dark matter acts like a cosmic glue, organizing the universe's structure and dictating the formation and movement of galaxies over billions of years. By understanding dark matter, we gain insights into the history and evolution of the cosmos itself. Researchers distinguish between dark matter and ordinary matter by observing how each interacts with light and gravity. Ordinary matter, which makes up stars, planets, and everything we see around us, emits, absorbs, and reflects light. This means it can be detected using telescopes and other instruments that measure electromagnetic radiation. In contrast, dark matter does not interact with light in any detectable way. It neither emits nor reflects light, making it completely invisible to traditional observational tools. Scientists suspect dark matter is out there because of its gravitational effects on visible matter. For example, when astronomers study galaxies, they notice that the stars on the outskirts revolve around the galaxy at speeds that would cause them to fly away if only visible matter were present. However, they stay tightly bound, indicating an unseen mass, dark matter, providing the necessary gravitational pull. To further differentiate between these two types of matter, researchers also look for the gravitational influence of dark matter in galaxy clusters. Here, the motion of galaxies can be analyzed as they move within a cluster, revealing that there's more mass at play than what we can see. Additionally, studying the cosmic microwave background, the faint afterglow of the Big Bang, offers clues about the existence and distribution of dark matter in the early universe. By combining these observations of gravitational effects with the dynamics of ordinary matter, researchers can piece together the makeup of the universe. This multifaceted approach ultimately helps to reveal the elusive nature of dark matter, showing us that while it may be invisible, its influence is a fundamental component of the cosmic landscape. Dark matter is one of the most intriguing mysteries in astronomy. Although it cannot be observed directly because it does not emit light or any form of electromagnetic radiation, scientists infer its presence through its gravitational effects on visible matter, such as stars and galaxies. Understanding dark matter is vital, as it constitutes a significant portion of the total mass of the universe. As we delve deeper into the cosmos, the implications of dark matter for future discoveries are profound. First, dark matter fundamentally shapes the structure and formation of galaxies. By influencing how galaxies are distributed, it helps define the large-scale architecture of the universe. Future studies may reveal new types of galaxies, or even previously undetected ones, which could change our understanding of both galaxy evolution and the universe's history. Additionally, dark matter affects the movement of galaxies. By studying how galaxies move, scientists can indirectly measure dark matter's influence. This pathway may lead to insights about the nature of dark matter itself. Is it made up of unknown particles or other exotic forms of matter? Each discovery could narrow down the possibilities, providing clues that propel physics toward a more comprehensive theory of matter. Moreover, upcoming telescopes and observational technologies aim to probe areas of space that were previously beyond our reach. As we observe more distant galaxies and structures, collecting data about their movements and interactions could yield evidence of dark matter's role on an even larger cosmic scale. The implications of dark matter extend beyond mere mystery. They are a gateway to understanding the universe in new and deeper ways. As researchers work to unravel this enigma, future astronomical discoveries may illuminate not only the nature of dark matter, but also fundamental questions about the origins and fate of the cosmos itself. Understanding dark matter is essential for grasping the overall mass of the universe because it plays a significant role in the structure and formation of galaxies. To put it simply, dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, we know it exists because of the gravitational effects it has on visible matter. Imagine the universe as a cosmic web, where galaxies are like nodes connected by strands of gravitational forces. When we observe galaxies, we see stars and gas, but we also notice that these galaxies rotate at speeds that should cause them to fly apart, if only the visible matter were present. This unexpected behavior indicates that there's more mass at play, mass that we cannot see. By studying how galaxies gravitate towards each other and how light bends around massive objects, scientists can infer the presence of dark matter. Essentially, it's like trying to feel the wind. We can't see it, but we can certainly feel its impact. Scientists estimate that dark matter constitutes a significant portion of the universe's total mass, much more than the ordinary matter we can detect. The study of dark matter is not just about filling in the gaps. It fundamentally shapes our models of the universe's evolution. Without dark matter, our understanding of cosmic history would be vastly incomplete, causing the current theories of galaxy formation and large-scale structure to fall apart. This invisible component helps explain why the universe behaves the way it does, pointing us toward a richer understanding of existence itself. As researchers continue to explore this elusive matter, they are piecing together the puzzle of the universe's true composition. Black holes are some of the most fascinating and mysterious objects in the universe, forming from the remnants of massive stars. When a star exhausts its nuclear fuel, it can no longer hold up against its own gravity. This leads to a dramatic collapse, creating a dense core. If the star is heavy enough, this core collapses further until it creates a black hole, an area of space where gravity is so strong that nothing, not even light, can escape from it. The forming of a black hole begins with the life cycle of a massive star. Throughout its life, the star fuses elements in its core, creating energy that counteracts gravitational pull. Once the fuel runs out, there's no energy pushing outward to balance gravity. The outer layers of the star may explode in a powerful event known as a supernova, leaving behind a dense core. If this core's mass is sufficient, it continues to collapse, leading to the birth of a black hole. Black holes have several key characteristics that set them apart. First, they possess an event horizon, which is the boundary around the black hole. It acts like a point of no return. Once something crosses this threshold, it cannot escape the black hole's pull. This creates a unique environment where space and time behave unusually. Inside the event horizon, the gravitational forces become incredibly strong, influencing the motion of everything nearby. Another notable feature is the singularity found at the center of a black hole. This is where the mass of the black hole is concentrated, and the laws of physics as we know them break down. While we can describe many aspects of black holes, the singularity remains one of the biggest mysteries in modern astrophysics. Black holes can vary in size and mass. Stellar black holes form from collapsing stars and usually contain a few times the mass of our Sun. However, supermassive black holes, which reside at the centers of most galaxies, including our Milky Way, can contain millions or even billions of solar masses. There are also intermediate black holes, whose existence is less understood. Understanding black holes not only provides insights into the nature of gravity and space-time, but also enhances our knowledge of the universe's evolution. Every time we study black holes, we uncover new layers of complexity, revealing just how much there is yet to learn about these enigmatic cosmic giants. The event horizon of a black hole serves as a critical boundary that marks the point of no return. Imagine it as a one-way door. Once you cross this threshold, there's no going back. At the event horizon, the gravitational pull of the black hole is so intense that it overcomes the escape velocity, meaning that nothing, not even light, can escape its grasp. This is why black holes appear black. They do not emit light that can reach us. As something approaches this boundary, it undergoes significant changes. For instance, if a star were to fall into a black hole, it would be stretched and compressed due to the difference in gravity between the side nearest to the black hole and the side farther away. This effect is known as spaghettification, as the object is pulled into a long, thin shape like spaghetti. For an outside observer, time seems to behave differently at the event horizon. As an object falls closer, it appears to move more slowly, almost freezing at the edge before gradually fading away from view. This is due to the time distortion caused by the black hole's strong gravitational field, where time stretches out significantly. To the person or object crossing the event horizon, however, they would pass through without noticing anything peculiar, or so it seems, as they would be oblivious to this stretching of time experienced by those outside. Inside the event horizon, the laws of physics as we understand them begin to break down, leading to profound mysteries about the nature of reality and the very fabric of the universe. Scientists have developed a variety of innovative methods to study the mysterious realms surrounding black holes. Since we cannot directly observe black holes themselves, due to their invisible nature, they focus on the effects these objects have on their surroundings. One primary way is through the study of light. When matter is drawn toward a black hole, it forms a disk that spirals inwards, heating up due to friction and emitting powerful radiation that can be detected by telescopes. This radiation, often in the form of X-rays, provides crucial clues about the black hole's mass, rotation, and the dynamics of the material around it. In addition to light, scientists use gravitational waves, which are ripples in space-time caused by massive objects, especially during dramatic events like black hole collisions. When two black holes merge, they produce these gravitational waves. Detectors around the world can capture these subtle signals. By analyzing them, researchers can glean information about the masses and spins of the merging black holes. Another fascinating approach involves the study of accretion disks. These are the swirling masses of gas and dust that form around a black hole. The properties of these disks reveal significant details. For instance, the speed of the gas can indicate how much mass is being drawn in and help infer the black hole's size and behavior. Finally, scientists are increasingly using computer simulations to model the complex physics around black holes. These simulations replicate the interactions of matter under extreme conditions, allowing researchers to visualize what is happening near a black hole, even if they cannot observe it directly. Together, these methods create a more extensive picture of these enigmatic celestial objects, revealing their secrets bit by bit. The Event Horizon Telescope, a network of radio dishes around the world, made groundbreaking discoveries about black holes by capturing the first image of one in 2019. This monumental achievement focused on the supermassive black hole at the center of our galaxy, known as Sagittarius A star, and another black hole in a distant galaxy called M87. Prior to this advancement, black holes were primarily theoretical concepts, inferred from the effects of their gravity on nearby stars and gas. However, the Event Horizon Telescope provided clear evidence of their existence by imaging the shadow or silhouette of the black hole against the bright backdrop of hot gas swirling around it. This shadow represents the point beyond which nothing can escape the black hole's gravitational pull, giving scientists a visual anchor to study. Additionally, the data collected allowed researchers to confirm that the size of these supermassive black holes aligns with theoretical predictions based on their mass, which is millions or even billions of times that of our Sun. Observations from the telescope also provided insights into the behavior of matter close to the event horizon, helping scientists understand how energy is emitted in the form of powerful jets that can influence galaxies at vast distances. Overall, these discoveries have not only reinforced our understanding of black holes, but also opened new avenues for research into the fundamental nature of gravity and the fabric of space and time itself. The work of the Event Horizon Telescope has marked a significant milestone in astrophysics, bridging the gap between theoretical predictions and observable phenomena in our universe. Black holes have a profound impact on their surrounding environments. They exert an incredible gravitational pull that can attract nearby matter, including gas, dust, and even entire stars. As this material spirals toward the black hole, it forms a disk known as an accretion disk. The intense gravitational force causes this matter to heat up, generating vast amounts of energy that can be emitted as light, often making the black hole visible to us as a bright source in the universe. Furthermore, this gravitational influence can shape the motion of stars and other celestial bodies nearby. Some stars may be pulled into a black hole's grasp, leading to spectacular events when they meet their end. This process can produce powerful explosions that are detectable across vast distances. On a larger scale, black holes can influence the dynamics of entire galaxies. The supermassive black holes at the centers of most galaxies, including our Milky Way, serve as anchors around which stars and other structures orbit. Their presence can affect star formation rates and contribute to the overall evolution of galaxies. By heating the surrounding gas and increasing turbulence in the interstellar medium, black holes can either trigger or suppress the birth of new stars. Moreover, when black holes collide or merge, they can release gravitational waves, ripples in the fabric of space-time, which can be detected across billions of light years and provide valuable information about the nature of the universe. Thus, Black holes are not simply dark, isolated phenomena. They are dynamic engines that shape their surroundings in powerful and fascinating ways. Supermassive black holes, often found at the centers of galaxies, play a significant role in shaping the evolution of their host galaxies. Imagine a supermassive black hole as a powerful engine that drives the growth and development of a galaxy over billions of years. When a galaxy forms, it contains a massive amount of gas and dust. The black hole's strong gravitational pull can attract this material, pulling it inward and creating a swirling disk of gas. As this gas spirals into the black hole, it heats up and emits a tremendous amount of energy, often observed as bright radiation. This energy output impacts the surrounding environment. Some of this energy can blow away gas and dust that would otherwise be available to form new stars. This process is known as feedback, and it helps control star formation rates within the galaxy. If the black hole is particularly active, it can prevent the galaxy from creating new stars, limiting its growth and shaping its structure over time. But if the black hole is quieter, more gas can settle into the galaxy, leading to bursts of star formation. Moreover, supermassive black holes can influence the dynamics of the galaxy as a whole. The gravitational forces exerted by the black hole affect the orbits of stars and gas within the central region of the galaxy. This can lead to a more organized structure, helping to stabilize the galaxy's rotation and overall shape. As galaxies collide and merge, supermassive black holes from each merging galaxy can also combine. These interactions can further regulate star formation and even lead to the development of more massive galaxies. Thus, supermassive black holes are not just a curious feature of galaxies. They are central players in the ongoing story of how galaxies evolve and transform across the vastness of space and time. At the heart of a black hole lies a singularity, a point where the laws of physics as we know them break down. Current theories propose that this singularity is where all the mass of the black hole is concentrated, creating an infinitely dense point that warps space and time to extreme degrees. According to general relativity, this is a concept in which gravity is so strong that nothing, not even light, can escape. One of the leading ideas about what occurs at the singularity involves quantum mechanics. This branch of physics describes the behavior of very small particles. Merging these two areas, general relativity and quantum mechanics, has proven challenging for scientists. Some theorists suggest that our current understanding of gravity and singularities is incomplete, and that a new, unified theory may reveal more about their nature. Another interesting perspective is the idea that the singularity could actually be a region of very high density rather than an infinitely small point. This theoretical approach separates itself from standard interpretations by proposing that the intense gravitational forces might create an environment where space behaves differently, potentially allowing for a multitude of outcomes. Additionally, there are hypotheses about the nature of time itself at the singularity. Some scientists speculate that, under extreme conditions, time could behave in unusual ways, even reversing or ceasing to exist as we understand it. While we have a good grasp of the effects of black holes on their surroundings, the true nature of singularities remains a mystery. As research continues, scientists are hopeful that advancements in technology and theoretical physics will reveal more about these enigmatic structures that challenge our comprehension of the universe. Gravitational waves are ripples in the fabric of space-time created by massive objects moving in extreme ways, particularly during catastrophic events like the collision of black holes. When two black holes spiral toward each other and finally merge, they release enormous amounts of energy, sending out gravitational waves that travel across the universe. These waves carry information about the events that generated them, much like sound waves carry information about a sound source. Scientists use highly sensitive instruments, like interferometers, to detect these waves as they pass through Earth. When a gravitational wave stretches or compresses space-time, it alters the distances between objects in a very precise way. By measuring these slight changes, researchers can confirm the existence of black holes and glean vital details about their properties, such as their masses and spins. Studying gravitational waves allows scientists to observe black hole interactions and mergers that would otherwise be completely invisible to traditional telescopes. This observation opens up a new avenue in astrophysics, providing insights into the formation and evolution of black holes, and even illuminating aspects of general relativity, the theory that describes gravitation. Thus, through the detection of these waves, we not only confirm the existence of black holes, but also deepen our understanding of how the universe works at its most mysterious and powerful scales. Black holes are pivotal players in the structure of the universe and the cosmic web. Imagine the universe as a vast, intricate web woven from the delicate threads of galaxies and dark matter. Black holes sit at various intersections within this web, influencing their surroundings in powerful ways. At the centers of most large galaxies, including our own Milky Way, reside supermassive black holes. These massive entities can be millions or even billions of times the mass of our Sun. Their gravitational pull is extraordinarily strong, affecting nearby stars and gas. This interaction helps to shape the dynamics of the galaxy, ensuring that stars orbit around the black hole rather than drifting aimlessly. Moreover, black holes can impact the formation and evolution of galaxies. During the early universe, when matter was concentrated in denser regions, black holes likely formed from collapsing stars. As they devoured surrounding material, they released tremendous amounts of energy in the form of radiation. This energy output can heat up nearby gas, influencing star formation. In some cases, it can even suppress the creation of new stars by pushing gas away, creating a balance that helps maintain the structure of the galaxy. On a larger scale, black holes contribute to the cosmic web by helping to shape clusters of galaxies. The gravitational forces they exert can aid in pulling galaxies together, forming clusters that are held in balance by the interplay of gravity and dark matter. The relationship between black holes and galactic structures is both dynamic and essential. They do not merely exist, but play an active role in the evolution of the universe. Additionally, the presence of black holes offers insights into the behavior of matter and the laws of physics under extreme conditions. Their existence challenges our understanding of space and time and raises questions about the fundamental nature of reality. Thus, black holes are not isolated features, but integral components that help define and influence the essence of the cosmos. Black holes stand as extraordinary enigmas in the universe, hinting at the deep laws of physics that govern our reality. They are not just cosmic vacuums. Rather, they are regions where the known rules of physics push against their limits. By studying black holes, scientists can examine the interplay between gravity, space, and time in ways that are otherwise impossible. At the core of a black hole lies a singularity, where matter is compressed to an unimaginably dense point. According to our current understanding, the laws of physics as we know them break down at this point. Investigating these regions can reveal how gravity interacts with the fundamental forces of nature. For example, scientists are eager to understand how the principles of quantum mechanics, the rules that govern the smallest particles, collide with the theories of relativity, which describe the larger structures of the universe. One particularly intriguing aspect of black holes is the information paradox. When something falls into a black hole, it seems that information about that object is lost forever. However, this challenge sparks questions about the nature of information and reality itself. If information cannot be destroyed, what does that mean for our understanding of reality? This paradox encourages scientists to rethink their concepts and may lead to breakthroughs in theoretical physics. Furthermore, black holes can produce waves in the fabric of space-time. These ripples, known as gravitational waves, provide another tool for investigation. When two black holes orbit each other and eventually collide, they release tremendous energy, which can be detected across vast distances. Observing these waves allows scientists to gather data about black holes indirectly, enhancing our understanding of their characteristics and behaviors. Black holes serve as a natural laboratory for exploring the fundamental laws of physics. As we uncover their mysteries, we draw closer to a more complete picture of how the universe operates, pushing the boundaries of human knowledge and revealing the deep connections between the very small and the vast. The Great Attractor is a mysterious region of space that has an immense gravitational pull, influencing the motion of galaxies in our cosmic neighborhood. To understand it, imagine a giant magnetic force that draws in everything nearby. This region is located in the direction of the Centaurus constellation, roughly 100 million light-years from Earth. Its exact nature is still somewhat elusive, primarily because it is obscured by the Milky Way's own stars and gas, making direct observations challenging. The discovery of the Great Attractor began in the 1980s when astronomers noticed that galaxies within our local group were moving towards a particular point in the sky. This unusual movement sparked curiosity among scientists, leading to extensive research. They found that the velocities of several galaxies differed from what would be expected based solely on the observable matter in the universe. This suggested that there was a large, unseen force behind these movements. As telescopes became more advanced, astronomers gained a clearer picture of the region. They deduced that the Great Attractor is not a single object, but rather a massive gravitational center formed by a concentration of galaxies, dark matter, and potentially other cosmic structures. Although the Great Attractor itself remains largely hidden from view, its gravitational influence on nearby galaxies allows scientists to infer its presence and importance in the greater cosmic web of the universe. The study of this enigmatic force continues, opening new doors to our understanding of the universe's structure and the forces at work within it. The Great Attractor holds a fascinating role in the cosmos as a gravitational anomaly that influences the motion of galaxies in our local region of the universe. Imagine the universe as a vast ocean filled with galaxies. Within this ocean, the Great Attractor acts like a massive underwater current, pulling nearby galaxies toward it with an invisible force. This feature is important for several reasons. First, it reveals the structure and dynamics of our universe on a grand scale. The Great Attractor serves as a center of mass that affects the movement of galaxies, including our own Milky Way, causing them to move towards it. This motion helps astronomers understand how galaxies interact and cluster together, providing insights into the gravitational forces that shape the cosmos. Moreover, the existence of the Great Attractor highlights the distribution of dark matter, an unseen form of matter that, while invisible, exerts a significant gravitational pull. Since we cannot directly observe dark matter, studying the Great Attractor becomes essential to piecing together the complex puzzle of what comprises our universe. Lastly, investigating this cosmic feature helps scientists explore the history of our universe. By examining the pathways and speeds of galaxies drawn toward the Great Attractor, we can glean valuable information about the early universe and how it has evolved over billions of years. Thus, the Great Attractor is not just a curious oddity, it is a key player in the intricate dance of galaxies and a crucial part of understanding our universe's fabric. The Great Attractor is a massive gravitational anomaly that lies in our local universe, influencing the motion of galaxies, including our own Milky Way. Imagine a giant cosmic magnet drawing objects toward it with its immense gravitational pull. This region of space contains a concentration of mass, including clusters of galaxies, and it impacts the trajectories of nearby galaxies as they travel through the universe. As the Milky Way and other galaxies move through space, they do not simply follow a straight path. Instead, they are affected by the gravitational forces of nearby massive structures. The Great Attractor is one such structure. Its gravitational field causes galaxies within a vast area to move towards it. This results in a flow of galaxies, all spiraling toward the center of this gravitational influence. The effect of the Great Attractor is particularly interesting considering the vast distances involved. The Milky Way, along with its neighbor galaxies, is on a journey that leads it closer to the center of the Great Attractor region. It is as if galaxies are in a cosmic dance, with their movements choreographed by the gravitational forces exerted by massive groups of galaxies clustered within the Great Attractor. Moreover, understanding the influence of the Great Attractor offers insights into the large-scale structure of the universe. It reveals how galaxies are not isolated islands, but part of a larger web, interconnected through gravitational forces. The ongoing movement of the Milky Way and other galaxies toward this gravitational center is a small glimpse into the dynamic and ever-changing nature of the universe. As we observe these movements, we uncover the intricate relationships between galaxies, shaping our understanding of cosmic evolution. The Great Attractor is a massive gravitational anomaly, influencing the motion of galaxies across a vast area of space. Observing it presents a unique challenge because of the cosmic foregrounds, such as the Milky Way galaxy, which can obscure our view. To peer through this cosmic clutter, astronomers employ several innovative methods. One primary technique is the use of different wavelengths of light. While visible light can be blocked by dust and gas in our galaxy, instruments designed to detect radio waves, infrared and X-rays can penetrate these obstacles more effectively. For instance, by observing in infrared, astronomers can see through the dust and identify the stars and galactic structures that lie between us and the Great Attractor. Another crucial method involves mapping the motion of galaxies. Observing it presents a unique challenge because of the cosmic foregrounds, such as the Milky Way galaxy, which can obscure our view. To peer through this cosmic clutter, astronomers employ several innovative methods. One primary technique is the use of different wavelengths of light. While visible light can be blocked by dust and gas in our galaxy, instruments designed to detect radio waves, infrared and X-rays can penetrate these obstacles more effectively. For instance, by observing in infrared, astronomers can see through the dust and identify the stars and galactic structures that lie between us and the Great Attractor. Another crucial method involves mapping the motion of galaxies. By analyzing how distant galaxies move, scientists can infer the gravitational pull of the Great Attractor, even if it isn't directly observable. They track the redshift of light from these galaxies, which indicates their speed and direction. This information helps paint a picture of how the gravitational forces are at play. Additionally, gravitational lensing is a phenomenon that astronomers utilize. When light from a distant object passes near a massive gravitational body, like the Great Attractor, it can be bent, causing those distant objects to appear distorted or multiplied. This lensing effect provides valuable information about the mass and distribution of dark matter around the Great Attractor. These techniques combine to help researchers look past the cosmic foregrounds, allowing them to piece together a more complete understanding of this intriguing region of space and its profound impact on the nearby universe. The Great Attractor is a massive region in space that exerts a strong gravitational pull on the galaxy cluster where we reside, known as the local group. This intriguing phenomenon suggests that mass in the universe is not evenly distributed. Instead, it points to areas of concentrated mass, drawing in surrounding galaxies and galaxy clusters. Imagine the universe as a vast ocean, where certain regions harbor enormous underwater mountains, creating gravitational whirlpools that suck in nearby ships. The Great Attractor acts similarly, revealing that there are dense clusters of galaxies within the universe, like the one at the core of the Great Attractor. This region is believed to contain a significant amount of invisible mass, often referred to as dark matter, that doesn't emit light or energy, making it difficult to detect directly. The presence of such structures alters our view of the universe, indicating that the cosmos has complex patterns where matter is clumped together in certain areas, leading to variations in gravitational forces. Understanding the Great Attractor, therefore, not only sheds light on how mass is distributed, but also helps us comprehend the dynamics of cosmic structures and the eventual fate of galaxies as they are influenced by these colossal gravitational influences. The Great Attractor is a massive gravitational anomaly located in the direction of the Centaurus constellation. Imagine it as a giant cosmic magnet pulling galaxies toward it. This enormous concentration of mass significantly influences the motion of galaxies over vast distances. What makes the Great Attractor especially intriguing is its connection to other superstructures, which are vast collections of galaxies and galaxy clusters that form a kind of cosmic web. One major connection is with the Laniakea supercluster, which is the home of our Milky Way galaxy. The Laniakea supercluster is not just a random assembly of galaxies. It is shaped by gravitational forces, including those from the Great Attractor. This means that as galaxies within Laniakea move, they are not only influenced by nearby clusters, but also by this distant gravitational pull from the Great Attractor. Furthermore, surrounding features like the Shapley supercluster also play a role in this dynamic. The Shapley supercluster is among the most massive clusters within the observable universe. Its own gravitational attraction interacts with that of the Great Attractor, contributing to the overall motion of galaxies in their vicinity. These interconnections illustrate the complexity of the universe's structure. The Great Attractor, along with other superstructures, forms a coherent framework of gravitational influence that shapes the arrangement and movement of galaxies. Understanding these connections helps scientists unravel the larger architecture of the cosmos, showcasing how everything is interconnected across staggering distances. Mapping the Great Attractor is a monumental challenge for astronomers. This vast gravitational anomaly is located in a region of space densely packed with galaxies, making it difficult to pinpoint the exact location of this unseen mass. First and foremost, it is situated behind the Milky Way, which means that our own galaxy obscures much of the view. This blocking effect creates a significant hurdle, as the stars and gas within the Milky Way can obscure the signals from distant galaxies that are essential for understanding the Great Attractor. Additionally, the Great Attractor exerts a huge gravitational pull on galaxies in its vicinity, causing them to move toward it. This motion, known as peculiar velocity, complicates how we interpret the data we collect. Astronomers must account for the natural movement of galaxies as they navigate the vast cosmic landscape, distinguishing it from the gravitational allure of the Great Attractor itself. Another hurdle is the distance involved. The Great Attractor is located millions of light-years away. The vastness of space means that details can be faint and hard to discern. Gathering data requires powerful telescopes and advanced techniques to detect the faint light from billions of stars in distant galaxies. Even with the best technology, astronomers can only observe a small portion of the full picture at a time. Lastly, understanding the distribution of dark matter in the universe adds another layer of complexity. Dark matter does not emit light, making it invisible and undetectable with traditional observational tools. However, its presence influences the movement of galaxies and groups of galaxies toward the Great Attractor. Part of the research involves inferring the location and amount of dark matter by observing how galaxies are drawn towards this gravitational center. Despite these challenges, astronomers continue to unravel the mysteries of the Great Attractor, employing innovative methods and tools to better understand this cosmic enigma and its role in the broader structure of our universe. The Great Attractor is a massive gravitational anomaly located within our universe, and it plays a significant role in how we perceive the expansion of the cosmos. To understand its influence, it helps to picture the universe as a vast and dynamic ocean. Just like currents can shape the movement of water, the Great Attractor draws galaxies towards itself with an immense pull created by its mass. As galaxies, including our own Milky Way, move toward this region, it creates a kind of localized distortion in how we observe the universe's expansion. Normally, we think of the universe as expanding uniformly, with galaxies moving away from each other. However, the Great Attractor introduces a powerful force that contradicts this general trend. Instead of all galaxies receding into the distance, those closer to this gravitational pull may have their movements altered, effectively distorting our interpretation of the universe's expansion rate as a whole. This situation leads to some exciting questions. Scientists must carefully analyze data from various distant galaxies to discern the true nature of this expansion, sifting through the influences of local gravitational pulls like those from the Great Attractor. When we study how galaxies are arranged and move, the pull from such a massive structure reminds us that the cosmos is not just expanding in one straightforward direction. Instead, it's an intricate dance of forces that creates variations we need to understand fully. In this way, the Great Attractor expands our understanding not only of how galaxies interact, but also of the complex nature of cosmic expansion itself. As we continue to explore and learn about these effects, we gain deeper insights into the universe's structure and evolution. The Great Attractor is a mysterious region in space that presents a fascinating challenge for astronomers. It appears to be a massive gravitational force that influences the motion of galaxies in its vicinity. To uncover its secrets, a variety of future observations and technological advancements are being planned. One of the key approaches includes using powerful telescopes equipped with advanced instruments. These telescopes will enable scientists to observe the faint light emitted by distant galaxies and gain a better understanding of their distribution and movement. By studying more galaxies in detail, researchers will be able to determine how they are affected by the Great Attractor's pull. Furthermore, space-based missions are also in the mix. Observatories stationed beyond Earth's atmosphere can provide clearer, uninterrupted views of the cosmos. This positioning allows astronomers to gather precise data about the structure and behavior of galaxies moving toward this enigmatic region. Scientists aim to utilize multi-wavelength observations, meaning they will collect information not just from visible light, but also from radio waves, infrared, and X-rays. Each type of observation reveals different aspects of astronomical objects. For instance, X-ray observations can help unveil the presence of hot gas around clusters of galaxies, indicating where gravitational forces are at play. In addition to telescopic advancements, simulations and computer models will play a crucial role. By inputting new data into these models, researchers can simulate the behavior of cosmic structures under various conditions. This will help them predict how the Great Attractor influences not only nearby galaxies, but also the larger structure of the universe. As these observations and technologies come together, astronomers hope to piece together the puzzle of the Great Attractor. Understanding this cosmic giant could shed light on fundamental questions about how galaxies interact and form in our universe. The Great Attractor is a mysterious region in space that exerts a powerful gravitational pull, influencing the motion of galaxies over vast distances. It is located about 200 million light-years away in the direction of the constellation Centaurus. To understand how this area draws in nearby galaxies, researchers have had to confront the enigma of dark matter. Dark matter is an invisible substance that makes up a significant part of the universe's total mass. Unlike normal matter, which we can see as stars and planets, dark matter does not emit or absorb light, making it undetectable with traditional telescopes. However, scientists know it exists because of its gravitational effects on visible matter. The interactions between the Great Attractor and surrounding galaxies provide clues about this elusive substance. As galaxies drift towards the Great Attractor, their paths are altered by the gravitational influence. This motion suggests that a considerable mass lies hidden in this region, likely in the form of dark matter. By studying the velocities and trajectories of galaxies, astronomers can infer the underlying structure of dark matter in the vicinity of the Great Attractor, piecing together information about how it is distributed and how much of it is present. Additionally, this intersection also sheds light on the large-scale structure of the universe. The way galaxies cluster around the Great Attractor reveals much about the fabric of the cosmos and the dynamics of gravitational forces at play. Observations and studies in this area help scientists understand not just the Great Attractor itself, but also broader cosmic phenomena that involve dark matter and the overall evolution of the universe. The Great Attractor serves as a critical point of investigation for understanding dark matter, linking the study of galaxy movements to the unseen forces that shape our universe. This relationship enriches our knowledge of cosmic structures and highlights the complex web of gravitational interactions that dominate at large scales. The discovery of the universe's expansion marked a profound shift in our understanding of cosmology, the study of the universe's origins, structure, and evolution. Before this discovery, many astronomers believed the universe was static, meaning it neither expanded nor contracted. Everything changed when Edwin Hubble observed that distant galaxies were moving away from us, and the farther they were, the faster they seemed to retreat. This observation led to a groundbreaking concept. The universe is not fixed but continually growing larger. The idea of universal expansion suggests that at one point, all matter and energy in the universe were concentrated in an incredibly small space, leading to an event often termed the Big Bang. This moment, thought to have occurred billions of years ago, initiated the dynamic evolution of the cosmos. Understanding that the universe is expanding opened the door to exciting questions about its fate. Would it keep expanding indefinitely, or would gravity someday pull everything back together? Moreover, this expansion revealed the presence of dark energy, a mysterious force thought to be driving the acceleration of this expansion. The realization that the universe's size and structure are ever-changing has led to advanced theories and models that seek to explain these phenomena in greater depth. Cosmology is now a field that interrogates how galaxies form, how stars live and die, and the very nature of time and space itself. The discovery of the universe's expansion was revolutionary because it transformed a previously static view of the cosmos into one of dynamic change. It prompted new thinking, leading to deeper explorations of the universe's beginning, its current state, and its ultimate fate, capturing the imagination of scientists and the public alike. Edwin Hubble was a revolutionary figure in astronomy, whose observations fundamentally changed our understanding of the universe. In the early 20th century, most scientists believed the universe was static, meaning that it neither changed in size nor moved. However, Hubble's work led to a groundbreaking realization: the universe is expanding. Hubble began by studying distant galaxies using a powerful telescope. He observed that these galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be retreating. This relationship suggested that the universe itself is growing larger over time. To demonstrate this, he measured the light coming from these galaxies. Light shifts in wavelength depending on how fast something is moving. This is known as the Doppler effect. Hubble found that the light from farther galaxies shifted towards the red part of the spectrum, indicating they were moving away from us. In addition to these observations, he formulated what is now known as Hubble's law, which states that the speed at which a galaxy moves away is directly related to its distance from us. This law provides the scientific basis for the concept of an expanding universe, implying that at some point in the past, the universe was much smaller and hotter, leading to the idea of the Big Bang. Hubble's findings not only altered our view of cosmos, but also opened up pathways for cosmology, leading scientists to explore the origins and ultimate fate of the universe. His work firmly established the universe as a dynamic entity rather than a static one, changing our perspective in profound ways. Cosmic expansion is the idea that the universe is growing larger over time. To measure this expansion, astronomers primarily look at how light from distant galaxies shifts as the universe stretches. This phenomenon is known as redshift. Imagine watching a train move away from you. The sound of its horn would lower in pitch as it gets farther away. Similarly, when light from galaxies moves away, it shifts towards longer wavelengths, which we perceive as redder. Astronomers observe distant galaxies and note how much their light is redshifted. This change can then be used to calculate their speed, how quickly they are moving away from us. The greater the redshift, the faster the galaxy is receding. To gather this data, scientists use powerful telescopes equipped with spectrographs, devices that split light into its components, allowing researchers to analyze the wavelengths. Both ground-based and space telescopes contribute to this process. Space telescopes like the Hubble Space Telescope avoid the distortion of the Earth's atmosphere, providing clearer and more accurate data. Other tools like the Very Large Array radio telescopes capture radio waves from celestial objects, offering another perspective on distance and speed. In addition, the cosmic microwave background radiation, the afterglow from the Big Bang, serves as a cosmic snapshot of the early universe. By studying its patterns and how they relate to the current expansion, scientists gain further insights into the rate at which the universe is stretching. Overall, measuring cosmic expansion combines observations of light, advanced technology, and theoretical models, all converging to deepen our understanding of the universe and its history. Redshift plays a vital role in our understanding of how the universe is expanding. Imagine a sound wave from a passing ambulance. As it approaches, the sound is high-pitched, but as it moves away, the sound decreases in frequency, becoming lower and more drawn out. This effect is similar to what happens with light. When we observe distant galaxies, their light appears stretched, moving toward the red end of the color spectrum. This shift toward red indicates that these galaxies are moving away from us. The further away a galaxy is, the greater the redshift we see, suggesting it is traveling away faster. This pattern shows that the universe is not just static, it is expanding. This discovery was a pivotal moment for astronomy, providing evidence that led to the formulation of the Big Bang theory, an idea explaining how the universe began with a singular, immense explosion and has been expanding ever since. By measuring redshift, astronomers can estimate the distances of galaxies and the rate of the universe's expansion. This movement away from us gives us clues about the nature of our universe and its history, illustrating that it is a dynamic, changing environment rather than a still backdrop for stars and planets. The Hubble constant represents the rate at which the universe is expanding. Imagine the universe as a balloon being inflated. As the balloon expands, the surface stretches, and points on the surface move away from each other. The Hubble constant helps us understand how quickly this separation is happening on a cosmic scale. This constant is crucial because it provides a measure of the universe's age and size. By observing distant galaxies and how fast they are receding from us, scientists can calculate how quickly the universe is growing. This information tells us not just about the present state of the universe, but also offers insights into its history and future. Understanding the Hubble constant allows astronomers to piece together the evolution of the cosmos. For instance, it reveals how long it has been since the Big Bang, the moment that marked the birth of the universe. Additionally, ongoing studies of this constant can help scientists unlock mysteries related to dark energy, a mysterious force that drives the accelerated expansion of the universe. As researchers refine measurements of the Hubble constant, it shapes our understanding of fundamental questions about the nature of space and time itself. The expansion of the universe is a fundamental concept in cosmology, describing how galaxies move away from each other over time. Scientists measure this expansion using a variety of techniques, but sometimes the results don't match up, leading to discrepancies that can be puzzling. One of the key methods to measure this expansion relies on observing supernovae, which are explosive deaths of stars. When these supernovae occur, they can be incredibly bright, allowing astronomers to judge their distances based on their brightness. Another method involves studying the cosmic microwave background radiation, a faint glow that fills the universe. This radiation gives clues about the early universe and influences estimates of its current expansion rate. However, when comparing results from these different methods, scientists have found inconsistencies. For instance, one technique might suggest the universe is expanding faster than another method indicates. Such differences pose significant challenges. They hint at the possibility that our understanding of physics on cosmic scales may need refinement. It raises questions about fundamental concepts such as dark energy, an invisible force believed to drive the acceleration of the universe's expansion. Additionally, these discrepancies can affect models of the universe. If measurements don't align, scientists must reconsider the assumptions they make about the universe's composition, structure, and future. It can feel like trying to solve a mystery where the pieces do not quite fit. Ultimately, reconciling these differences could open doors to new physics, potentially leading to groundbreaking revelations about how the universe works and what it is made of. This ongoing pursuit highlights the dynamic nature of science, where questions lead to deeper exploration and understanding of the cosmos. The expansion of the universe has a significant impact on the light that reaches us from distant galaxies. Think of the universe as a balloon being inflated. As the balloon expands, the dots on its surface, representing galaxies, move away from each other. The farther a galaxy is from us, the faster it appears to be moving away. This movement affects the light that these galaxies emit. When a galaxy emits light, that light typically travels towards us. However, as the galaxy moves away, the wavelengths of that light get stretched out. This phenomenon is called redshift. Imagine a sound source like a train whistle moving away from you. The sound changes pitch. Light from galaxies behaves similarly, but instead of a change in sound, we see a shift in color. The light moves from the blue end of the spectrum towards the red end as the wavelengths become longer. Not only does the redshift inform us about the speed of a galaxy's movement, but it can also tell us about the age of the universe and help scientists understand its evolution. The farther we look into space, the more we are looking back in time. As we observe these distant galaxies, we see their light stretched out, revealing crucial information about the cosmos's expansion and the forces driving it. This stretching of light does not merely indicate distance, it also impacts the brightness and the properties of what we observe. Some galaxies, once vibrant and blue when they emitted their light, can appear red and dim by the time it reaches our instruments, masking their true characteristics. Understanding this expansion helps astronomers decode the universe's history and the fascinating processes that govern its growth. The future of the universe is closely tied to its expansion rate, which influences how galaxies move apart and how cosmic structures develop over time. Currently, the universe is expanding, and scientists have observed this expansion is accelerating. This acceleration is attributed to a mysterious force known as dark energy. One potential future scenario is called the Big Freeze. If the current rate of expansion continues, galaxies will drift further apart over vast stretches of time. Eventually, stars will burn out, and the universe will grow increasingly cold and dark. In this scenario, the universe could reach a state where it is nearly empty, with only faint remnants of stars and galaxies remaining, leading to a bleak and icy expanse. Another possibility is the Big Rip. In this scenario, if dark energy continues to increase in its repulsive effect, the expansion could become so rapid that it tears apart galaxies, stars, planets, and even atoms themselves. This would result in a chaotic end where everything in the universe is pulled apart. Conversely, there's the Big Crunch, which assumes that the expansion could someday reverse. If the total mass of the universe is sufficient to halt its expansion, gravitational forces could cause it to start collapsing back on itself. This would lead to all matter being drawn together into a single dense point, ultimately leading to a state similar to the one that preceded the Big Bang. Lastly, there could exist a stable universe where the expansion rate slows down significantly but never quite stops. This would result in a universe that grows very old but remains somewhat stable, allowing for a slower evolution of cosmic structures without an eventual dramatic end. The future of the universe can take on various forms based on the characteristics of its expansion. Whether it leads toward a lonely, cold void, an energetic disintegration, a dramatic collapse, or a quiet longevity, our understanding of cosmic physics continues to evolve, shaping how we envision what lies ahead. The Lambda CDM model is a powerful framework that helps us understand the structure and evolution of our universe. To grasp how it describes the universe's expanding nature, we start with the idea that the universe is not static. Instead, it is constantly growing, with galaxies moving away from each other over time. This expansion can be visualized as a balloon being inflated, where the surface represents space itself. As the balloon inflates, points on the surface move further apart. Central to this model is the concept of dark energy, represented by the Greek letter lambda. Dark energy acts as a driving force behind the acceleration of the universe's expansion. Think of it as a mysterious energy that permeates all of space, pushing galaxies apart and causing the rate of expansion to increase over time, like blowing air into a balloon that expands faster the more air you add. Alongside dark energy, the model includes cold dark matter, which contributes to the gravitational framework that shapes galaxies and large structures in the universe. While dark matter is not directly observable, its presence is inferred through the gravitational pull it exerts on visible matter, like stars and galaxies. On a larger scale, the Lambda CDM model suggests that the universe began with an event known as the Big Bang, which provided the initial conditions for all structure and expansion. Since that moment, the expansion has continued, and it's the balance between the gravitational effects of matter and the repulsive nature of dark energy that determines how this expansion behaves. Researchers use observations of distant galaxies, cosmic microwave background radiation, and other astronomical phenomena to test and refine this model. The cumulative evidence supports the idea that the universe is expanding consistently and accelerating, guided by the intriguing dynamics between dark energy and matter. Through the Lambda CDM framework, we gain insight into not only how the universe expands, but also its ultimate fate, which remains one of the most fascinating questions in cosmology. Understanding the expansion of the universe is one of the most exciting areas of modern astronomy. Several missions are currently underway, each using different techniques to investigate this phenomenon. One notable mission is the James Webb Space Telescope, which was designed to observe distant galaxies and their light as it traveled billions of years through space. By studying these old galaxies, researchers hope to gather data on the rate at which the universe is expanding and how that expansion has changed over time. Another important mission is the European Space Agency's Euclid satellite, set to launch soon. Euclid will map out the shape of galaxies and their distribution across the universe. By examining how these galaxies are spread out, scientists can glean insights into the forces driving the expansion, including mysterious dark energy, which is thought to influence the universe's growth. Additionally, there are ground-based telescopes like the Vera C. Rubin Observatory in Chile, dedicated to observing transient phenomena. Its large survey will help create a comprehensive map of the sky, allowing scientists to track supernova and other cosmic events. By measuring the distances to these events and how fast they are receding from us, they can refine their understanding of the universe's expansion rate. Together, these missions provide a multifaceted view of how the universe is changing. They combine light from the past with our current observations, weaving a deeper narrative about not just where we are in the universe, but how we got to be here and where we are headed. Each new discovery leads to more questions and helps to deepen our understanding of the cosmos. In a cosmic context, time is perceived quite differently than in our everyday lives. On Earth, we typically measure time using clocks, with hours and minutes marking our daily activities. This familiar rhythm gives us a sense of time flowing at a steady pace. However, in the vastness of the universe, time behaves in more complex ways, influenced by speed and gravity. When we look at objects moving close to the speed of light, time appears to stretch. Imagine a person traveling in a spaceship at this extraordinary speed. For them, time would pass normally, but observers back on Earth would see their clock ticking slower. This leads to a fascinating idea where the traveler could journey for what feels like a short time, while many years pass on Earth, a phenomenon known as time dilation. Gravity also plays a crucial role in how time is experienced. In areas with strong gravitational fields like near a black hole, time slows down significantly. Picture it as a heavy weight placed on a spring. The stronger the weight, the more the spring compresses and stretches, affecting how quickly it can move, just like how time ticks differently in various gravitational conditions. This means that a clock closer to a massive object would tick more slowly compared to one farther away. Overall, while we experience time in a direct and familiar way in our daily lives, in the broader cosmic arena, the flow of time is influenced by speed and gravity, creating a tapestry of differing perceptions. Each key event in the universe, from the tick of a distant star's clock to our everyday moments, contributes to the intricate understanding of time as not just a linear path, but a dynamic element of reality itself. The beginning of time in the universe is a profound subject that has intrigued scientists and philosophers alike. One of the most leading theories is the Big Bang theory. This concept suggests that the universe started from an extremely hot and dense state and then expanded rapidly. Imagine a tiny balloon that is completely deflated and packed tightly. When you blow air into it, the balloon inflates and grows larger. Similarly, the universe expanded from this initial point, giving rise to everything we see today: space, time, matter, and energy. In the moments right after the Big Bang, the universe was incredibly small, so small that it existed in a state where traditional physics does not apply. This is often thought of as a singularity, a point where our understanding of time and space breaks down. As time began to unfold from this event, the universe cooled, allowing particles to form, which eventually combined to create atoms, stars, galaxies, and all the complex structures that exist. Another interesting idea to explore is the concept of cyclic universes. This theory suggests that rather than a single beginning, the universe goes through cycles of expansion and contraction, with each cycle representing a new beginning and end. Think of it like a heartbeat, expanding and then contracting. Every cycle could set the stage for a new universe, each time starting fresh. Another intriguing concept is the idea that time itself emerged with the universe. Before the Big Bang, some theorists propose that there was no time as we understand it today. Instead, time could have started simultaneously with the expansion of space, meaning that asking what happened before the Big Bang may not make sense, as time as a dimension was not yet in existence. These theories offer fascinating glimpses into the origins of our universe, but much remains uncertain. Ongoing research and exploration aim to peel back the layers of these mysteries, providing deeper insights into how everything began. Each theory adds a piece to the puzzle, enhancing our understanding of time's intricate relationship with the cosmos. Relativity reshapes our perspective on time and space in significant ways. Before Einstein's theories, time and space were seen as constant and unchanging, much like a rigid backdrop for the events of the universe. However, relativity introduces the concept that both time and space can stretch and bend depending on speed and gravity. Imagine that time flows like a river, and each person experiences its flow differently. If someone travels fast, close to the speed of light, for example, time for them slows down compared to someone who remains stationary. This means that two people, one traveling quickly and one at rest, can age at different rates. The faster you move, the slower time passes for you relative to someone who is not moving. This is known as time dilation. On the other hand, space itself is also influenced by speed and gravity. When a massive object like a planet or a star is present, it creates a sort of dent or curve in the fabric of space. This is why planets orbit stars. They are following the paths determined by this warped space. Consequently, the deeper you go into a gravitational field, the more pronounced the alteration of space and time becomes. Combining these ideas gives us a dynamic view of the universe. Instead of seeing time and space as fixed entities, we understand them to be interconnected and malleable. Events can appear to take different lengths of time for different observers, and the distance between 2 points can change based on their gravitational context. Thus, relativity reminds us that our cosmic existence is far more intricate and surprising than we once thought, revealing the universe as a fluid interplay of time and space that shapes everything within it. Time dilation occurs when objects are near massive bodies, such as planets or stars. To understand this concept, imagine time as a flexible fabric affected by gravity. The stronger the gravitational pull, the more this fabric stretches and bends. When an object is close to a massive body, it experiences a difference in time compared to an object that is far away. For example, think about two clocks, one placed near a huge planet and the other positioned far out in space. The clock next to the planet would tick more slowly compared to the one in deep space. This means that if someone were to spend a significant amount of time near that planet, they would age less than someone who stayed away. This effect has practical implications for space travel. If astronauts were to journey close to a black hole, where gravity is incredibly strong, they would find that time flows much more slowly for them compared to someone remaining far away. This means that if they returned from such a journey, they could find that years have passed on Earth, even though they experienced only a short period themselves. These implications stretch beyond just theoretical discussions. They affect satellite technology and global positioning systems, which must take time dilation into account to provide accurate readings. Without adjustments for this effect, everyday navigation would be thrown off, leading to errors in determining positions on Earth. Thus, time dilation is not merely a fascinating aspect of physics. It plays a crucial role in our understanding of the universe and our practical experiences within it. Black holes and wormholes stir our imagination when we think about the possibilities of cosmic time travel. Let's start with black holes. These mysterious entities exist where gravity is so strong that nothing, not even light, can escape. As we venture closer to their event horizon, the boundary surrounding them, time behaves in unusual ways. For an outside observer, time flows smoothly, but for someone falling into a black hole, it appears to slow down dramatically. This implies that if one were to survive the journey through a black hole and emerge on the other side, the experience of time could be drastically different compared to the world outside. This has led scientists to ponder whether a journey through a black hole might allow a traveler to leap forward into the future. Now, turning to wormholes, which are theorized to be shortcuts through space and time, they introduce a more direct concept of time travel. Imagine a tunnel that connects two distant parts of the universe. If such a tunnel exists, it could allow someone to travel vast distances instantly, effectively altering the flow of time experienced by the traveler. The fascinating aspect is that if these tunnels have connections at different times as well as locations, they might provide a means to travel backward in time. However, whether wormholes exist and can be navigated safely is still a matter of speculation. Both concepts offer intriguing possibilities for understanding time and space. They challenge our perception of time as a constant, suggesting that under certain conditions, it might be more flexible than we realize. Yet while these ideas inspire wonder and curiosity, actual time travel remains one of science's greatest mysteries, bordered by the needs for extreme conditions and our current technological limitations. To explore the fabric of space-time, scientists have embarked on various groundbreaking experiments that delve deep into the workings of the universe. One of the most notable experiments is the observation of gravitational waves, which are ripples in space-time caused by massive objects like merging black holes or neutron stars. By detecting these waves, scientists can confirm predictions made by the theory of relativity, which describes how gravity influences the structure of space and time. Another key experiment involves atomic clocks. Scientists have placed these incredibly precise timekeepers at different altitudes, such as on the ground and in high-flying airplanes. The results show that clocks at higher altitudes tick slightly faster than those closer to the Earth. This discrepancy occurs because the gravitational pull is weaker farther from the mass of the Earth, illustrating how gravity can warp time itself. Additionally, the phenomenon known as the time dilation effect has been tested using particles called muons. These particles decay at a certain rate, but when they are created in the upper atmosphere, they travel toward the Earth at near light speeds. Because of their high velocity, their lifespan appears to increase for observers on the ground, highlighting how movement through space can influence the passage of time. Scientists have also utilized large particle accelerators, where particles are accelerated to speeds close to that of light. As these particles move rapidly, their behaviors support the theories predicting that effects on space and time occur. Such experiments tap into the fundamental relationships between matter and the fabric of space-time. Through these various methods, researchers gather evidence that not only reinforces existing theories, but also opens doors to new questions about the universe. Each experiment adds another layer of understanding about how space and time are intertwined, showcasing the fascinating complexities of our cosmos. Quantum mechanics and general relativity are two foundational frameworks in physics, but they operate in very different realms and describe the universe in distinct ways. General relativity deals with the forces of gravity and the structure of large-scale spacetime, providing a comprehensive explanation of how massive objects like planets and stars warp the fabric of space around them. Think of this concept as a heavy ball lying on a stretched rubber sheet. The sheet dips and curves around the ball, illustrating how matter influences the geometry of space-time. On the other hand, quantum mechanics addresses the behavior of tiny particles, such as atoms and subatomic particles. It reveals a world where particles can exist in multiple states at once, and where their properties are not precisely defined until they are measured. This unpredictability leads to phenomena that are as strange as they are fascinating, such as particles appearing to be in two places at the same time or influencing each other instantaneously over vast distances. The challenge arises when trying to combine these two theories into a single unified understanding of the universe. While general relativity works wonderfully at explaining the movement of galaxies and the expansion of the universe, it falters when we examine the extreme conditions near black holes or the moments after the Big Bang. In these scenarios, the effects of quantum mechanics become significant, but general relativity does not account for them. Imagine trying to fit together two very different puzzles that don't share any pieces. The mathematics of quantum theory involves probabilities and uncertainties, while general relativity relies on precise measurements of space and time. The result is a complex conflict that scientists have been striving to resolve. Attempts to formulate a theory of quantum gravity aim to create a bridge between these fields, allowing us to understand space-time dynamics at all scales, from the tiniest particles to the largest cosmic structures. This quest for a merged theory is one of the frontier challenges in modern physics, with the potential to deepen our understanding of the universe and answer fundamental questions about how space, time, and matter coexist. The cosmic horizon acts like a boundary in the universe that shapes our understanding of both time and space. Imagine standing on a vast beach, looking out at the ocean. The horizon represents what you can see. The farther you look, the more distant the scenes become. Similarly, the cosmic horizon defines the limits of what we can observe in the universe, influenced by the speed of light and the age of the universe. As we gaze deeper into the night sky, we are not just looking at stars and galaxies, we are peering back in time. The light from these celestial objects takes a long journey to reach us, sometimes millions or even billions of years. Because of this, the farther away we look, the earlier we see the universe, revealing how it once was. The cosmic horizon marks the point beyond which the light has not yet had time to reach us, and beyond that limit, there is still so much universe left unseen. This boundary also affects our understanding of space itself. As the universe expands, regions that are currently observable may eventually drift beyond our cosmic horizon. Over time, as galaxies move away from us faster than light can travel, they effectively vanish from our view, creating a constantly changing landscape. This dynamic nature of the cosmic horizon illustrates how our perception of time is intertwined with the vastness of space. The cosmic horizon is not just a physical limit, it represents the ever-evolving relationship between observation, time, and the immense scale of the universe. Every glimpse we take at the cosmos uncovers the history of galaxies and stars, tying our existence to the expansive fabric of the universe itself. Cosmic inflation is a fascinating idea that speaks to the very origins of our universe. It refers to a rapid expansion that occurred just moments after the Big Bang, when our universe was incredibly small and dense. In this brief period, the universe expanded faster than the speed of light. Now, this might sound impossible because nothing can exceed light speed according to our current understanding, but in the realm of cosmic inflation, it is the fabric of space itself that stretches. To visualize this, think about a balloon being blown up. As the balloon inflates, the surface expands. Similarly, during cosmic inflation, the universe expanded, stretching the space between all points. This rapid stretching changed not only the distances between galaxies, but also affected how we understand time itself. When space expands so quickly, it also alters the relative flow of time. Regions of space that were once close together stretched so far apart that they became invisible to each other, leaving an imprint on the universe's structure we still see today. Cosmic inflation reshaped both space and time, setting the stage for the cosmos we observe. It created the uniformity we see in the cosmic microwave background radiation and influenced the large-scale arrangement of galaxies. Understanding inflation allows us to piece together the timeline of the universe, connecting the exceedingly small moments after the Big Bang to the vastness we now witness, reinforcing the idea that space and time are intertwined in ways that continue to astonish scientists and enthusiasts alike. New technologies are revolutionizing our understanding of space and time, unlocking mysteries that have long puzzled scientists. One of the most significant advancements comes from powerful telescopes. These telescopes allow us to see distant galaxies, stars, and even planets orbiting other stars at incredible distances. By capturing light that has traveled for millions or even billions of years, we can study the early universe and gain insights into how it has evolved over time. Another exciting development is in the field of simulations and computer modeling. These tools enable scientists to recreate conditions of the universe in a controlled environment. By manipulating variables like gravity and time, researchers can explore how cosmic events unfold. For instance, they can simulate black holes and understand better how they warp space-time, helping us comprehend the fabric of the universe itself. Moreover, advancements in quantum technology are adding new dimensions to our exploration. Quantum sensors, for example, are incredibly sensitive instruments that can detect minute changes in gravitational fields. This ability has potential applications ranging from understanding how matter behaves near a black hole to detecting gravitational waves produced by colliding massive objects, adding more pieces to the cosmic puzzle. Finally, robotics and artificial intelligence are aiding both unmanned space explorations and missions to Mars. Rovers equipped with advanced sensors and cameras gather data about the Martian landscape, providing insights that inform our understanding of not just Mars, but also the history of our solar system. As these technologies continually improve, they enhance our capability to study the complex interactions of space and time. With every new discovery, we get closer to unlocking the secrets of the universe, prompting us to question not just where we are in space, but how time itself is intricately woven into the cosmos. Cosmic inflation is a theory that describes a brief, rapid expansion of the universe just after the Big Bang. To understand this, imagine the early universe as a tiny, hot, and dense point. In the blink of an eye, this point expanded tremendously, much faster than the speed of light. This event took place in a fraction of a second, transforming the minuscule universe into a vast expanse. This sudden stretch helped shape the universe we observe today. During cosmic inflation, regions of space that were once very close together became incredibly far apart. ensuring that the universe's large-scale structure developed uniformly. It also explains why the cosmos is so smooth and homogeneous, like a perfectly blended smoothie, despite containing tiny variations that later became stars and galaxies. Inflation solves several key puzzles about the universe's early development. For instance, it addresses why different parts of the sky look similar, a phenomenon known as the horizon problem. Since the universe expanded so quickly, regions that are now very distant had been in close contact before inflation, allowing them to share information and energy. Furthermore, this process can account for the slight irregularities we see in the cosmic microwave background radiation, which is the afterglow of the Big Bang. These irregularities eventually led to the formation of galaxies and other structures we see today. Cosmic inflation paints a picture of a swiftly evolving universe, laying the groundwork for the intricate cosmos we continue to explore. The theory of cosmic inflation was primarily proposed by the physicist Alan Guth in the early 1980s. The motivation for this groundbreaking idea came from several unresolved issues in the standard model of cosmology, which describes the birth and evolution of the universe. Before inflation, scientists struggled to explain why the universe appears remarkably uniform in temperature and density across vast distances, even though these regions should not have been able to influence each other due to the limitations imposed by the speed of light. This puzzling uniformity is known as the flatness problem, and it raised questions about how the universe managed to maintain such consistency. Furthermore, observations indicated that the universe's expansion rate had been slowing down over time, hinting at gravitational forces pulling matter back together. Yet at the same time, there were signs that the universe contained an enormous amount of unseen matter, challenging scientists to understand how all these elements fit together. Guth introduced cosmic inflation as a solution to these issues, suggesting a brief event in the universe's earliest moments where a tiny region expanded at an incredible rate, far faster than the speed of light. This rapid expansion would have smoothed out any irregularities, leading to the uniformity we observe today. Moreover, the theory elegantly explains the current flatness of the universe and provides a framework for understanding its large-scale structures. Overall, cosmic inflation not only resolved these significant puzzles, but also sparked a new era in our understanding of the universe. The concept of inflation in cosmology addresses several complex issues in the Big Bang model, one of which is the horizon problem. To understand this issue, consider that the universe appears remarkably uniform in temperature and structure, even across vast distances. This seems puzzling because light from distant regions hasn't had enough time to travel to us since the beginning of the universe. Therefore, how can these far-apart areas have the same temperature? Inflation proposes that in the very early moments of the universe, it expanded rapidly, much faster than the speed of light. During this brief period, regions that were once close together were stretched out across the cosmos. Imagine taking a small balloon and blowing it up quickly. The points marked on the balloon's surface, which were previously close, suddenly become widely spaced apart. Right after this rapid expansion, the universe returned to a more normal expansion rate. This swift inflation helped to smooth out variations in temperature and density because any minuscule fluctuations were spread uniformly across a much larger area. As a result, when we look at the universe today, we see those once closely connected regions that have maintained a consistent temperature and structure, even though they are now impossibly far apart. Inflation creates a scenario in which the very early universe was microscopically small and uniform, allowing subsequent expansion to keep those characteristics intact, thus elegantly solving the horizon problem. The idea of cosmic inflation suggests that the universe went through a period of extremely fast expansion just after the Big Bang. Several pieces of evidence support this fascinating theory. One key piece lies in the uniformity of the cosmic microwave background radiation. This faint glow, spread evenly across the sky, represents the remnant heat from the early universe. The remarkable consistency in temperature throughout this background suggests that regions that are now far apart were once close together, helping explain how they could end up so uniform. Another compelling piece of evidence is the distribution of galaxies throughout the universe. Observations show that galaxies are not randomly scattered, but instead form a web-like structure. This arrangement points to a rapid expansion that would have stretched and smoothed out any initial irregularities in the early universe. If inflation occurred, it would have amplified these uneven patches, leading to the clumpy distribution we observe today. Additionally, scientists have analyzed fluctuations or tiny variations in the cosmic microwave background. These fluctuations indicate differences in density that eventually led to the formation of galaxies and large-scale structures. These small deviations are consistent with predictions made by inflationary models, suggesting that the universe's early rapid expansion influenced these later structures. Lastly, advanced observations of gravitational waves provide another layer of support. These waves are ripples in spacetime created by massive events in the universe. Certain patterns in these waves could indicate interactions and phenomena from the time of inflation, giving further credence to the idea that a rapid expansion took place. Together, these various pieces of evidence form a strong case for the existence of a rapid inflationary period, painting a detailed picture of our universe's origins and its subsequent evolution. Cosmic inflation serves as a key chapter in our understanding of the early universe, explaining why the universe appears so uniform and smooth. To grasp this, imagine the universe just after the Big Bang. At that time, it was a tiny, hot, and dense point. Just moments later, it underwent a rapid expansion, almost like a balloon being blown up. This expansion stretched the fabric of space at an incredible speed, causing regions that were once close together to move far apart. Now consider the cosmic microwave background, which is the faint glow left over from that early hot state of the universe. It is like a snapshot of the universe when it was only a few 100,000 years old, revealing how energy and matter were distributed at that time. The remarkable aspect of the cosmic microwave background is its uniformity. It looks almost the same in every direction we observe. Inflation provides a reason for this uniformity. During its brief moments of rapid expansion, any small differences in temperature or density were smoothed out, much like how a mixing process evenly distributes ingredients in a batter. As a result, the regions that we eventually observe today in the cosmic microwave background were stretched to such great distances that they could not influence one another. Thus, when inflation ended, these regions shared a similar temperature and density, leading to the uniform appearance we see in the cosmic microwave background today. In short, cosmic inflation acted as a cosmic equalizer, allowing the early universe to expand rapidly and creating the foundation for the uniformity we observe in the afterglow of the Big Bang. This connection highlights how the intricate processes that shaped the universe are crucial in understanding its current structure. The idea of multiple inflationary periods in the universe suggests that different regions might have undergone rapid expansion at different times. To understand this, let's first consider the concept of inflation itself. Inflation refers to a very brief moment after the Big Bang, when the universe expanded exponentially, growing faster than the speed of light and smoothing out irregularities. If inflation happened multiple times, it could mean that our observable universe is just a small bubble in a much larger space. Each inflationary event might create its own distinct bubble, leading to regions of varying characteristics. Some of these bubbles may end up with different laws of physics or distinct forms of matter, resulting in a multiverse, a vast collection of universes, each with its own unique properties. This scenario leads to intriguing possibilities. For instance, if different bubbles have different physical laws, they could host entirely varied forms of life or no life at all. It introduces the idea that our universe might not be the only one, but rather a part of a larger cosmos where conditions vary wildly. Additionally, these multiple inflationary events could help explain why our universe appears so uniform. The rapid expansion during inflation would have smoothed out any initial irregularities, leading to the homogeneity we observe today. If there were regions that expanded after different initial conditions, these could show us the diverse behaviors and outcomes of inflationary processes. Finally, studying potential multiple inflationary periods aids astronomers and physicists in understanding cosmic evolution and the fundamental forces that shape reality. It poses significant questions about the origins of structure in the universe and challenges our grasp on the very nature of existence. Exploring this theory encourages deeper investigation into both the early universe's behavior and what lies beyond the observable limit. Scientists simulate cosmic inflation by using theoretical models that apply the principles of physics to understand how the universe expanded rapidly after the Big Bang. During inflation, which is believed to have occurred just moments after the universe began, space itself expanded much faster than the speed of light, causing small regions to stretch immensely. To create simulations, researchers often start with the fundamental theories of particle physics and general relativity. They develop mathematical equations that describe how energy, pressure, and temperature interact in a very young universe. These equations help to model the behavior of the tiny, fluctuating energy fields that would have triggered inflation. Next, scientists use computer simulations to visualize how these energy fields evolve over time. By inputting variables like density and energy distribution, they can create a virtual universe where inflation takes place. The simulations allow scientists to observe how slight variations in these initial conditions can lead to different cosmic outcomes, influencing the formation of galaxies, stars, and other structures we see today. Moreover, researchers also compare their models with observational data. They look at the cosmic microwave background radiation, which is the afterglow of the Big Bang, to see if their simulated outcomes match what we observe in the universe. This comparison helps refine the models, making them better at explaining the complex processes involved in cosmic inflation. Overall, these simulations not only enhance our understanding of the early universe, but also allow scientists to explore the possibilities of what might have happened during that extraordinary expansion. Investigating the inflationary epoch presents researchers with numerous challenges, largely due to the nature of the event itself and the limitations of our observational tools. The inflationary epoch refers to a fraction of a second after the Big Bang, during which the universe expanded rapidly, far faster than the speed of light. This incredible speed means that any direct observation of that time is beyond our reach, since light from that era cannot be captured now. One key challenge is the lack of direct evidence from that period. Most of the information we have about the early universe comes from the cosmic microwave background radiation, which is like an afterglow of the Big Bang. This radiation offers hints but doesn't provide a full picture of the inflationary phase. Researchers must rely on complex models and theoretical frameworks to infer what occurred, which can lead to uncertainties. Another difficulty arises from the need for precision in measurements. Scientists are searching for specific patterns in the cosmic microwave background and other celestial phenomena that could confirm inflationary predictions. These patterns, known as imprints, can be faint and easily masked by other cosmic signals or noise, making it essential to develop sophisticated instruments and techniques capable of isolating this delicate data. Moreover, inflationary models themselves propose various ways that inflation might have unfolded, each leading to different predictions. The challenge lies in distinguishing between these competing theories based on the available observations. This chaotic mix of possibilities complicates the search for consensus within the scientific community. Finally, interdisciplinary collaboration is crucial for tackling these issues, as understanding the inflationary epoch requires insights from different fields like particle physics, quantum mechanics, and cosmology. Coordinating these diverse areas effectively presents another layer of complexity. All these hurdles underscore the ongoing quest to unravel the mysteries of the universe's beginnings, highlighting both the ambition and ingenuity of researchers in the field. Cosmic inflation is a theory that suggests the universe underwent a rapid expansion just moments after the Big Bang, vastly increasing its size in an incredibly short period. Understanding this concept is crucial, as it helps explain the uniformity of the cosmos we observe today. However, as scientists explore deeper into the cosmos, future discoveries could challenge or refine this understanding in several ways. One potential avenue for new insights is through advanced technology, such as more powerful telescopes. These could allow us to observe the farthest reaches of the universe and gather data on the oldest light, known as the cosmic microwave background radiation. By examining tiny fluctuations in this radiation, scientists can gather clues about the conditions and physics at play during inflation. Discovering new patterns or unexpected elements within this data could lead to adjustments in our inflation models. Additionally, computational simulations of the early universe are becoming increasingly sophisticated. By experimenting with various physical conditions and forces, researchers may uncover scenarios that produce outcomes aligning more closely with observational data. If new simulations suggest alternative theories, they may alter the currently accepted view of inflation or introduce additional phenomena that need to be considered. Another transformative discovery could involve gravitational waves, ripples in spacetime generated by massive accelerating objects. As more understanding emerges from experiments designed to detect these waves, they may reveal links to the inflationary period. If gravitational waves from the early universe can be observed or measured, they could offer direct evidence supporting or refuting various inflation models. Lastly, the potential existence of new particles or fields in high-energy physics could open the door to redefining fundamental forces in the universe. The creation of specific conditions in laboratories to explore these possibilities might lead us to re-evaluate how inflation occurred and its implications for the universe's overall structure and fate. As we advance our observational technologies, enhance our computational models, and explore high-energy physics, we stand on the brink of discoveries that could reshape our understanding of cosmic inflation, revealing deeper truths about the universe's origin and evolution. Each new piece of evidence could lead to monumental shifts in how we perceive the cosmos, underscoring the dynamic nature of scientific inquiry. The concept of an inflationary universe radically reshapes our understanding of both the universe and our place within it. At its core, inflation suggests that the universe underwent a rapid expansion shortly after the Big Bang, expanding faster than the speed of light. This idea leads to profound philosophical discussions about infinity, existence, and the fundamental nature of reality. First, consider the nature of space and time. If the universe can stretch beyond boundaries we can comprehend, it challenges our traditional views of a finite universe. We may think of everything within the cosmos as interconnected, but inflation implies that there could be regions of space that are forever unreachable. This notion nudges us to confront the limitations of human perception and understanding. If the universe can expand infinitely in scale, what does that say about our place within it? Moreover, the idea of a multiverse arises from inflationary theory. If inflation can happen multiple times, it may create a vast number of disconnected universes, each with its own set of physical laws and constants. This leads to questions about necessity and chance. Are we simply a random occurrence in this broader tapestry? It provokes reflections on purpose and meaning. Are we special because we exist in one of these universes, or is existence itself just a product of random conditions? Additionally, the implications extend to the nature of observation and knowledge. In an inflationary universe, much of what we may wish to understand could be fundamentally beyond our observational reach. This highlights the distinction between what we can know and what is intrinsically real. Are there truths about the universe that remain forever inaccessible to us? Such questions invite a deeper exploration of the limits of science and the pursuit of knowledge. An inflationary universe not only provides a framework for understanding cosmic development, but also pushes us to explore deeper philosophical issues regarding existence, the nature of reality, and the pursuit of scientific understanding. It fundamentally alters how we perceive ourselves within the universe, opening a tapestry of existential questions that resonate beyond the realms of science. The multiverse theory is a fascinating idea, suggesting that our universe might be just one of many, possibly an infinite number of universes that coexist. Imagine our universe as a single bubble in a vast ocean filled with countless other bubbles, each representing its own universe with unique laws of physics, distanced from our own. This concept arises from several different scientific frameworks. One of the main sources of the multiverse idea is the theory of cosmic inflation. After the Big Bang, the universe is believed to have experienced an extraordinary expansion, stretching rapidly. Some scientists theorize that this inflation could happen in different regions of space simultaneously, leading to the production of many isolated bubbles or universes, each stopping inflation at different times and evolving independently. Another avenue that encourages the multiverse theory comes from quantum mechanics. In simple terms, when particles have multiple possible outcomes, they can theoretically split into different realities, each reflecting a different outcome. This branching creates a multitude of varied universes that diverge based on these decisions. Additionally, string theory, which attempts to describe all fundamental forces and particles, often leads to a multitude of possible configurations and dimensions, each of which could correspond to a different universe. These various frameworks suggest that our universe isn't unique. Instead, it may simply be one of countless environments, each existing with different versions of physical laws and realities. While the multiverse theory expands our understanding of existence, it also presents challenges in terms of evidence and testability, leaving it at the edge of scientific exploration rather than established fact. The concept of the multiverse comes from the intriguing intersections of string theory and quantum mechanics, both of which revolutionized our understanding of the universe. To start, string theory proposes that the fundamental building blocks of everything we see are not particles like tiny balls, but rather tiny vibrating strings. These strings can twist and vibrate in different ways, and their various forms generate the diverse particles and forces we observe. Interestingly, string theory requires additional dimensions beyond the familiar three of space and one of time we experience daily. This leads to the idea that our universe might be just one of many that exist within this higher dimensional space. On the other hand, quantum mechanics introduces a different perspective on reality. In the quantum world, particles can exist in multiple states at once until measured or observed. This principle suggests that every possible outcome of a quantum event is realized in separate, branching realities. For example, in a simple coin flip, instead of just landing heads or tails in a single reality, quantum mechanics implies that there are universes where it lands heads and others where it lands tails. Combining these ideas, the multiverse emerges as a natural consequence. In this view, not only could there be multiple universes governed by their own set of physical laws, but string theory also indicates that the shape and behavior of these additional dimensions could lead to an infinite variety of possibilities. Each universe could have different properties, constants, and perhaps even forms of life, making the multiverse a vast and diverse landscape of reality. Therefore, through the lens of string theory and the principles of quantum mechanics, the multiverse concept invites us to imagine a reality that is far more complex and populated than anything we can perceive with our senses, pushing the boundaries of scientific exploration and our understanding of existence itself. The multiverse theory proposes a fascinating idea. Our universe may be just one of many, each with its own unique characteristics. Imagine a vast library filled with countless books, where every book tells a different story about how reality could be. Some of these universes might be nearly identical to ours, while others could be drastically different. One potential form is the bubble universe. Think of our universe as a bubble floating in a larger space filled with numerous bubbles, each representing a different universe. Each bubble could have different physical laws. For example, one bubble might allow the existence of different kinds of particles or forces, leading to completely different forms of matter and life. Another intriguing form is the parallel universe, where every decision leads to a branching path. In this scenario, for every choice made, a new universe could develop, each reflecting a different outcome. You might exist in one universe where you chose one path, while another version of you follows a completely different direction in an alternate universe. There are also universes that could exist with entirely different dimensions. Our universe has three familiar dimensions of space and one of time. However, some theories suggest that other universes could possess additional dimensions, leading to realities we cannot fully comprehend. These dimensions could change how time functions or how forces interact, resulting in bizarre and unpredictable phenomena. Lastly, some theorists speculate about universes governed by different fundamental constants. In our universe, certain quantities like the strength of gravity or the charge of an electron are precise. But in another universe, these values could be altered, causing the basic fabric of that reality to differ greatly, possibly even leading to a universe where atoms as we know them couldn't exist. The multiverse opens the door to incredible possibilities, each universe representing a different arrangement of physical laws, dimensions, and histories. This invites us to ponder the nature of existence itself and the infinite potential of reality. Bubble universe models suggest a fascinating way of thinking about the cosmos and the potential existence of multiple universes, or a multiverse. Imagine our universe as just one bubble in a vast cosmic foam. Each bubble represents a different universe, formed through processes that occur during a phase of rapid expansion in the early universe, known as cosmic inflation. In these models, inflation starts in a particular region of space, causing it to expand rapidly. This rapid expansion creates varying pockets, much like bubbles in boiling water. Each pocket continues to grow, and within those bubbles, different physical laws or constants may develop. This means that every bubble universe could have its own unique properties, varied from ours or from each other. The environments within these bubbles are shaped by the specific conditions present at their formation. Some might have the right conditions for stars and planets, while others may be completely inhospitable. The idea proposes that if bubbles can form and separate, then there can be countless universes existing simultaneously, each with different characteristics. This creative view not only challenges our understanding of the universe, but opens up compelling questions about what else might exist beyond our observable reality. Thus, bubble universe models serve as a framework for imagining that the cosmos is far bigger and more diverse than we can currently perceive, possibly filled with universes that differ in ways we can only begin to explore. The concept of a multiverse suggests that our universe is just one of many, potentially with different physical laws and constants. Evidence that could support this idea often comes from areas of physics and cosmology. For instance, the theory of cosmic inflation, which proposes that the universe expanded rapidly after the Big Bang, implies that different regions of space might have gone through this process at different times, effectively creating multiple bubbles of universes. If we could observe patterns or irregularities in the cosmic microwave background radiation, which is the afterglow of the Big Bang, it might hint at interactions between these separate universes. On the other hand, evidence that could refute the multiverse idea involves the principles of testability and observation. For something to be considered scientifically valid, it typically needs to be observed or measured. Since other universes may lie beyond our observational reach, some scientists argue that believing in a multiverse may not be scientifically rigorous. Essentially, if we cannot gather information or evidence about these other universes, it raises questions about their existence as a scientific theory. Another piece of the puzzle comes from fine-tuning in our universe. The very specific conditions that allow for the existence of life could suggest that there might be many universes with varied properties where only a small fraction are capable of supporting life. However, the question of whether this fine-tuning is due to a multiverse or simply a single universe with some fortunate conditions remains unanswered. The discussion around the multiverse is intricate, with supporting evidence emerging from theories of cosmic inflation and fine-tuning, while the challenges lie in the lack of direct observational evidence and the need for a testable framework. As research continues, scientists hope to clarify whether we are truly alone in this universe or just one of many. The anthropic principle helps us explore why the universe appears finely tuned for life. It suggests that the physical laws and constants we observe are compatible with the existence of life because we are here to notice them. This concept raises fundamental questions about our own existence in a universe that seems so perfectly arranged for life to thrive. When combined with multiverse theory, the anthropic principle gains an intriguing dimension. The multiverse theory proposes that there could be an immense number of universes, each with different laws of physics and varying constants. Imagine these universes as bubbles in a vast cosmic sea, where each bubble represents a unique universe that might have entirely different properties. In this context, the anthropic principle suggests that we find ourselves in a universe where conditions just happen to support life. If many universes exist, some will have the right balance of forces and constants for life to emerge, while countless others will not. Therefore, it's not surprising that we live in a universe that allows us to observe and ponder our existence. We only observe the one where life is possible. This connection opens a fascinating dialogue about our place in the cosmos. It implies that while we may ponder the deeper reasons for existence and the universe's fine-tuning, the reality of being here might simply be a product of the vast tapestry of universes where life can occur in specific settings. Thus, the anthropic principle, when viewed through the lens of multiverse theory, invites us to reflect not just on our own universe, but also on the infinite possibilities that lie beyond it. Testing the multiverse hypothesis presents significant hurdles for scientists. The core idea of the multiverse is that our universe may be just one of many, each existing in its own separate reality. This concept stretches the limits of what we can observe and measure, making it difficult to confirm through traditional scientific methods. One of the main challenges is that other universes, if they exist, are beyond the reach of our instruments. We can observe only what happens within our universe. Any evidence from another universe is, at best, indirect and speculative. This limits our ability to conduct experiments or observations that could provide concrete proof. Moreover, the assumptions and predictions about the multiverse often arise from theories in physics that themselves are not yet fully established. For instance, theories in string theory or cosmic inflation suggest the possibility of a multiverse. But these theories can be mathematically complex and are hard to test in a clear, straightforward way. Scientists must distinguish between what can be tested within our universe and what remains pure speculation. Additionally, even if we could gather evidence of the multiverse, it raises profound philosophical questions about the nature of scientific inquiry. Do we modify our understanding of science to accommodate realms that we cannot observe? This debate keeps the scientific community engaged in exploring whether the multiverse is a scientifically valid idea or simply a fascinating theoretical construct. These challenges create a picture where the multiverse remains a tantalizing possibility, but one that is currently beyond the horizon of empirical science. As our tools and theories advance, the landscape of exploration may change, yet for now, researchers continue to navigate through these complex issues, searching for answers to one of the most profound questions about existence. The concept of the multiverse suggests that our universe might be just one of many, potentially infinite universes. To explore this idea, different branches of physics work together, each contributing its unique tools and perspectives. Firstly, cosmology, the study of the universe's origin and structure, plays a significant role. Cosmologists use observations of the cosmic microwave background radiation, which is the afterglow of the Big Bang, to explore the conditions that led to the universe we see today. Through this, they can hypothesize about scenarios that might create other universes. Then, quantum physics enters the discussion. This field deals with the behavior of the smallest particles. Quantum mechanics introduces the notion of superposition, where particles can exist in multiple states at once. Some interpretations of quantum mechanics suggest that every choice leads to a branching of reality, creating parallel universes for each outcome. This idea broadens the understanding of what a multiverse could entail. Next, string theory provides yet another layer. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. This theory allows for extra dimensions beyond the familiar three of space and one of time. Some string theory models predict a landscape of possible universes, leading to the concept of a multiverse containing various types of universes, each with its own laws of physics. General relativity, the theory that explains gravity's effect on space and time, also contributes to the understanding of the multiverse. It describes how mass and energy warp spacetime. This framework can help theorize how different universes might exist with different spacetime geometries. Finally, these branches do not function in isolation. They interact creatively through theoretical studies, mathematical models, and even computer simulations. Physicists collaborate on experiments that test these ideas, attempting to find signs of other universes. Each branch of physics reinforces the others, providing a comprehensive toolkit for investigating phenomena beyond our own universe. In this collaboration, the multiverse concept transforms from pure speculation into a scientifically rich and fascinating field of inquiry. While many questions remain unanswered and further evidence is needed, the combined efforts of these different branches of physics continue to push the boundaries of our understanding of reality itself. The multiverse theory presents a captivating concept that challenges our traditional view of existence and reality. Imagine our universe as a single bubble in a vast ocean filled with countless other bubbles, each representing a different universe. Each of these universes might have its own unique set of physical laws, dimensions, and conditions. This means that in some universes, things could be remarkably different from what we experience in ours. Now consider the implications of this idea. Our understanding of existence shifts dramatically. Instead of being the single reality, we could be one of many, each universe creating its own version of events. This could mean there are worlds where different choices were made, leading to alternative histories and futures. For instance, the life you lead might be vastly different in another universe where a key decision took a different path. The multiverse theory also invites us to think about the fundamental nature of reality itself. It suggests that our universe might just be a product of chance among infinite possibilities. This challenges the notion of a universal truth, as each universe could operate under its own set of rules. Such a framework makes the fabric of reality much richer and more complex, allowing for different forms of existence that we may not even be able to envision. Furthermore, engaging with this theory encourages scientists and philosophers alike to explore questions about what it means to exist. If there are infinite versions of ourselves, what defines our identity? Are we merely products of our universe's specific parameters, or is there something more universal that connects all of existence? In contemplating the multiverse, we expand our horizons beyond the boundaries of what we know, igniting curiosity about the nature of our own reality and our place within it. It opens a doorway to infinite possibilities, asking us to rethink everything we know about existence. The concept of a multiverse suggests that there may be multiple, perhaps infinite universes existing parallel to our own, each with different versions of reality. This idea transforms philosophical discussions in profound ways. If every choice we make might lead to a different version of ourselves in another universe, it provokes questions about free will and destiny. Are our decisions truly ours if alternate paths exist elsewhere? This notion can make individuals re-evaluate their sense of agency and the significance of their actions. Ethically, the multiverse perspective might encourage a broader understanding of consequences. If there are countless realities, could it be argued that actions have different moral weights across different universes? For instance, a decision considered wrong in our universe might lead to an alternate outcome in another. This could alter how people approach moral reasoning and ethical dilemmas, shifting focus from absolute truths to a more relativistic view of ethics. Furthermore, the multiverse concept contributes to existential questions about meaning and purpose. Knowing that there are countless alternate lives could lead some to feel that their existence is less special or unique. Others might find comfort in the idea that every possible life they could live is playing out somewhere. Ultimately, embracing the multiverse challenges individuals to reconsider their beliefs about life, responsibility, and the universe's complexity, sparking deeper conversations about existence itself. The cosmic microwave background, often referred to as the CMB, is the faint glow of radiation that fills the universe and presents a snapshot of the early stages of our cosmos. Imagine a time about 380,000 years after the Big Bang, when the universe was still very hot and dense. At that point, particles were too energetic, preventing light from traveling freely. However, as the universe expanded, it cooled, allowing protons and electrons to combine to form hydrogen atoms. This process created a cascade of photons or light particles that could then travel through space. The CMB is essentially the remnant of that early light, now stretched into the microwave range of the electromagnetic spectrum due to the expansion of the universe. It can be detected today as a uniform background radiation that is remarkably even across the entire sky, punctuated only by slight fluctuations. These variations are crucial because they reveal information about the density of matter and energy in the early universe and provide clues about how structures like galaxies and clusters formed over time. In cosmology, the CMB serves as a vital tool for understanding the fundamental properties of the universe. By studying its temperature fluctuations and patterns, scientists can glean insights into the universe's age, composition, and the rate of its expansion. It also supports the Big Bang theory, providing strong evidence that the universe has not always looked the way it does today. The existence of the CMB confirms our understanding of how the universe evolved and opens windows to explore mysteries such as dark matter and dark energy, which comprise much of the cosmos yet remain largely unknown. As such, the CMB is not just a relic of the past, it is a cornerstone of modern cosmology, shaping our understanding of the universe's history and destiny. The discovery of the cosmic microwave background radiation, or CMB, was a pivotal moment in our understanding of the universe's origins. This radiation fills the universe and is a remnant of the Big Bang, a crucial event where the universe began to expand. The CMB was first discovered in the 1960s by two radio astronomers, Arno Penzias and Robert Wilson. They were working with a large radio antenna in New Jersey, expecting to observe radio signals from the Milky Way. Instead, they detected a persistent background noise that seemed to come from all directions. Even when they tried to eliminate various sources of interference, including removing pigeon droppings from their antenna, they could not clear this mysterious signal. Penzias and Wilson's initial confusion turned into excitement when they learned about the theoretical predictions of the Big Bang and how such radiation should have filled the universe. Their discovery provided strong evidence for this theory and earned them a Nobel Prize. Today, scientists use advanced instruments to study the CMB and understand the early universe better. One of the most significant tools is the Wilkinson Microwave Anisotropy Probe, often referred to as WMAP. Launched in 2001, WMAP mapped slight temperature fluctuations in the CMB across the sky, revealing vital information about the universe's age and composition. Another important satellite is the Planck spacecraft, launched in 2009, which gathered even more precise data about the CMB, allowing scientists to delve deeper into the universe's structure and evolutionary history. These observations help us to uncover the mysteries of cosmic inflation, dark matter, and dark energy, shaping our understanding of the cosmos today. The cosmic microwave background, or CMB, is like a snapshot of the universe taken when it was just a baby. Imagine the universe as a very hot and dense ball of gas filled with particles and radiation. This state existed around 380,000 years after the Big Bang. At this time, the universe began to cool down, allowing electrons and protons to combine and form hydrogen atoms. When this happened, the dense fog of particles cleared, and light could finally travel freely through space. The CMB represents this light, the first we could ever see from our universe. By studying the CMB, scientists gain critical insights into the conditions of the universe when it was young. It carries information about its temperature, density, and distribution of matter. Tiny fluctuations in the CMB reveal variations in density that became the seeds for galaxies and other structures we see today. These fluctuations indicate how clumpy or smooth the universe was, shedding light on how it developed over billions of years. Furthermore, the CMB tells us about the overall composition of the universe. It helps scientists understand how much ordinary matter, and dark energy make up the cosmos. The uniformity of the CMB across the sky shows that the universe is mostly homogeneous at large scales, while the slight variations offer clues about the gravitational forces that formed stars and galaxies. Overall, the CMB acts as a map of the universe's early state, helping us piece together a cosmic history that stretches back to its very beginnings. The cosmic microwave background radiation, often called the CMB, is like a snapshot of the universe when it was just about 300,000 years old. Back then, the universe was a hot, dense place filled with energy and particles, and as it expanded, it cooled down. As it did, protons and electrons came together to form hydrogen atoms, allowing light to travel freely for the first time. This light has continued to journey through space and is what we now detect as the CMB. When scientists study the CMB, they look for tiny fluctuations in its temperature. Though these differences are incredibly small, they serve as important clues about the early universe. You can think of these temperature fluctuations as the ripples on the surface of a pond after a stone is thrown in. Some areas are slightly warmer or cooler than others, which indicates where matter was slightly more concentrated. These fluctuations are crucial because they tell us about the distribution of matter in the universe and how it influenced the formation of galaxies and larger structures. Regions that were slightly denser ended up attracting more matter due to gravity. Over billions of years, those small differences in density grew, leading to the clusters of galaxies and vast cosmic voids we see today. So, by examining the CMB, scientists gain insights into the forces at play in the early universe that set the stage for everything we observe now, crafting the large-scale structure of the cosmos that is so intricate and beautiful. The cosmic microwave background, or CMB, is a crucial piece of evidence supporting the Big Bang theory. Imagine the universe as a balloon being inflated. As it expands, everything inside it moves further away from each other. In the very early stages, the universe was exceptionally hot and dense, similar to an intensely glowing fireball. As it expanded, it cooled, which allowed particles to form atoms and ultimately light to be released. The CMB represents this light, now stretched and cooled, filling the universe like an echo from its hot beginnings. Detected from every direction in space, it appears almost uniform, but very small temperature differences hint at the early universe's structure. These fluctuations helped seed the formation of galaxies. By studying the CMB, scientists can gather information about the rate of expansion of the universe, its overall composition, and its age. The presence of this ancient radiation is not just a coincidence. It matches the predictions of the Big Bang theory and provides a way to understand the universe's history and its evolution over billions of years. Thus, the CMB acts like a time capsule, revealing secrets from just after the dawn of time and cementing our understanding of how the universe came to be. The cosmic microwave background, or CMB, is a faint glow of radiation left over from the Big Bang that fills the universe. Understanding the polarization patterns within the CMB can provide crucial insights into the early moments of our universe, specifically during the period known as inflation. During inflation, the universe underwent a rapid expansion. This expansion stretched tiny quantum fluctuations into larger regions of space, creating the seeds for all structures we see today. When we look at the CMB, we find that its light is not just uniform, it has a specific polarization pattern. This means that some of the light waves are aligned in particular directions rather than being scattered randomly. These polarization patterns fall into two main types: E-mode and B-mode polarization. E-mode is more common and results from regular density fluctuations. However, the B-mode polarization is especially intriguing because it might be linked to gravitational waves, which are ripples in space-time that could have been produced during the inflationary period. By analyzing the intricate patterns of both E-mode and B-mode polarization in the CMB, scientists can gather evidence about the physics that governed the universe at that time. If B-mode polarization is detected at certain levels, it may support the theory of inflation and provide clues about the characteristics of the inflationary process itself, such as how fast inflation occurred and what forces or particles were at play. Essentially, studying these polarization patterns is like peering back in time to understand the universe's earliest and most formative moments. The cosmic microwave background, or CMB, is a faint glow permeating the universe, left over from the Big Bang. It holds many secrets about the early moments of our universe, but several mysteries still puzzle scientists. One significant question revolves around the exact nature of the fluctuations seen in the temperature of the CMB. These slight variations indicate where matter was denser and eventually formed galaxies. The challenge is understanding why these fluctuations exist at the specific scales observed. Another mystery is related to the strange patterns in the polarization of the CMB. This polarization carries information about gravitational waves, which are ripples in space-time. Scientists are particularly interested in whether these waves emerged from cosmic inflation, an event theorized to have taken place right after the Big Bang. If so, detecting these signals could uncover details about the universe's expansion. Additionally, there's the enigma of dark matter. The CMB provides evidence for its existence, but the exact nature of dark matter remains elusive. What is it made of? How does it interact with regular matter? These questions continue to spark intense research in the field. Finally, the CMB also hints at a mysterious force called dark energy, believed to be driving the universe's accelerated expansion. The properties and implications of dark energy remain poorly understood, leaving scientists eager to unlock that mystery. Each of these unresolved questions holds the potential to reshape our understanding of the universe and its origins, signaling that there's still much to learn from the CMB. The cosmic microwave background, or CMB, is like a faint afterglow of the Big Bang, providing a snapshot of the universe just a few 100,000 years after its birth. Research into the CMB has made remarkable strides, largely due to advances in technology over the past few decades. In the beginning, scientists used simple radio receivers to detect this weak radiation, which made it challenging to gather clear data. As technology progressed, The development of more sophisticated instruments allowed researchers to capture more detailed images of the CMB. One of the major breakthroughs was the launch of satellite missions, such as the Cosmic Background Explorer, which was introduced in the late 1980s. This satellite was equipped with highly sensitive detectors that could measure temperature fluctuations in the CMB across the entire sky, revealing tiny variations that provide clues about the early universe's structure. Subsequent missions, like the Wilkinson Microwave Anisotropy Probe, benefited from improved detectors and data analysis techniques. These advancements enabled scientists to create detailed maps of the CMB, uncovering essential information about the universe's age, composition, and the presence of dark energy. In recent years, even more advanced telescopes have been developed, both on the ground and in space. With high-resolution detectors and sophisticated methods for data processing, researchers can now probe finer patterns in the CMB. This ongoing evolution of technology is opening new doors for understanding fundamental questions about the universe, such as its expansion and the nature of the forces that shaped its earliest moments. The latest projects, like the Polarized Radiation Imaging and Spectroscopy mission, are utilizing cutting-edge technology to explore additional features of the CMB, focusing on polarization, the direction the light waves oscillate. This polarization offers insights into the conditions of the early universe, including processes like inflation, a rapid expansion that occurred right after the Big Bang. The journey of CMB research has been greatly enhanced by technology. Each evolution in instrumentation and data analysis brings scientists closer to uncovering the mysteries of the universe's origins and its ongoing development, revealing a deeper understanding of our cosmic home. The Cosmic Microwave Background, or CMB, serves as a relic of the universe's early moments, providing invaluable clues about its past, present, and future. Formed just after the Big Bang, the CMB consists of faint remnants of heat that permeate all of space. It offers a snapshot of the universe about 300,000 years after its creation, when atoms began to form, allowing light to travel freely. Analyzing the CMB reveals the density and distribution of matter and energy in the early universe. This information helps scientists understand the universe's expansion rate. If we consider the universe as having been set into motion with a certain speed after the Big Bang, the way that speed changes over time can hint at its ultimate fate. The CMB also shows the slight variations in temperature across different regions of space. These fluctuations indicate where matter clumped together to form galaxies and clusters. By studying these patterns, scientists can learn about the overall geometry of the universe. A flat universe suggests that it will expand forever at a slowing rate, while a closed universe might eventually collapse back on itself. Additionally, the CMB's properties reveal the influence of dark energy, an unknown force believed to be driving the acceleration of the universe's expansion. If dark energy remains constant or increases, the universe may continue to expand forever, leading to a fate where galaxies drift apart and stars eventually burn out. In contrast, if dark energy were to decrease, the universe could stop expanding and begin contracting, leading to a possible scenario known as the Big Crunch, where everything eventually collapses into a singular state. Thus, the CMB acts like a cosmic map, guiding researchers as they piece together the puzzle of how the universe might evolve over vast stretches of time. Its insights into the structure, expansion, and energy of the universe speak to the complex interplay of forces that could determine its ultimate fate. The Cosmic Microwave Background, or CMB, is like a snapshot of the universe from its infancy, taken around 380,000 years after the Big Bang. It holds clues about the early universe, and scientists carefully analyze this ancient light for patterns and irregularities. Anomalies, which are unexpected features or variations observed in this data, prompt scientists to dig deeper. When researchers encounter these anomalies, they start by checking for errors in their measurements. It's crucial to confirm that these irregularities are not just artifacts created by the instruments or the methods used to collect data. If the anomalies are verified, scientists consider a range of explanations. They might explore whether the anomalies indicate new physics beyond what current theories predict. For example, strange patterns could suggest the influence of structures that we have yet to fully understand, or maybe offer hints of phenomena like gravitational waves from cosmic events. Another avenue of interpretation involves examining how these anomalies fit into cosmic inflation theories. which propose that the universe underwent an incredibly rapid expansion shortly after the Big Bang. Some anomalies might support or contradict these theories, leading scientists to refine their models of the universe's evolution. Ultimately, understanding these anomalies is a collaborative effort involving astronomers and physicists across the globe. They analyze, debate, and test ideas, hoping that clues in the CMB data will unveil more about the universe's origin, its composition, and the fundamental forces at play. Each anomaly represents not just a puzzle, but also an exciting opportunity to tap into the vast mysteries of our cosmic history. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They can originate from various sources, including the Sun and other more distant cosmic events like exploding stars, which we call supernovae. When these particles collide with the Earth's atmosphere, they create showers of secondary particles which can be detected on the ground. The story of their discovery begins in the early 20th century. Scientists were puzzled by mysterious radiation that couldn't be explained by the known sources of radiation on Earth. In the year 1916, a physicist named Victor Hess made significant contributions. He conducted a series of balloon flights, taking detectors high into the atmosphere. As he ascended, he noticed that radiation levels increased, providing clear evidence that more radiation existed beyond the Earth's surface. This radiation was not just from natural sources like the Earth itself, but was coming from outer space. Hess concluded that this must be originating from cosmic sources, leading to the term cosmic rays. His groundbreaking work earned him a Nobel Prize in 1930, solidifying cosmic rays' place in the study of high-energy astrophysics. Today, cosmic rays remain a crucial area of research as scientists continue to uncover their origins and effects on our planet. High-energy cosmic rays are thrilling particles that originate from deep space. When these particles, often protons or atomic nuclei, enter Earth's atmosphere, they encounter molecules in the air at incredibly high speeds. This interaction sets off a chain reaction. As the cosmic ray collides with an atmospheric molecule, it creates a shower of secondary particles. First, the impact can break apart the incoming particle and the target molecule. This release results in new particles including pions and muons, as well as other lighter particles like electrons and positrons. These secondary particles then continue to interact with the atmosphere, generating thousands of additional collisions. These reactions mostly happen high above the ground, typically at altitudes of about 15 to 25 kilometers. By the time the shower of particles descends towards the surface, they have weakened significantly. Very few of these secondary particles actually reach the ground. Most lose energy through additional collisions as they pass through the air. Interestingly, some of the particles that do reach the surface can be detected by sophisticated instruments. These instruments help scientists study cosmic rays and their sources. Overall, the interaction of high-energy cosmic rays with Earth's atmosphere not only illuminates the mysteries of the universe, but also plays a crucial role in our planet's natural processes. Ultra-high-energy cosmic rays are among the most energetic particles known in the universe, and they can originate from a variety of fascinating astrophysical sources. One prominent source is supernovae, which are explosive deaths of massive stars. When these stars end their lives, they release vast amounts of energy, creating shock waves that can accelerate particles to incredibly high speeds. These accelerated particles can then escape into space, contributing to cosmic rays. Another potential source is active galactic nuclei, which are essentially massive black holes at the center of galaxies that actively consume material. The energy around these black holes can propel particles to extreme velocities, producing cosmic rays that travel across the universe. Similarly, gamma-ray bursts, intense flashes of gamma radiation resulting from the collapse of massive stars or the merging of neutron stars, are strong candidates as sources of ultra-high-energy cosmic rays. The explosive energies involved are immense, providing the right conditions for particle acceleration. Additionally, powerful jets produced by pulsars and magnetars, which are types of neutron stars, can also create cosmic rays. As these celestial objects spin and emit strong magnetic fields, they can accelerate particles to high energies. Furthermore, the collision of cosmic rays with interstellar matter can also produce secondary ultra-high energy particles, adding to the dynamic environment of the universe. Collectively, these sources contribute to a complex and intriguing picture of where ultra-high-energy cosmic rays originate, illustrating the incredible forces at play in the cosmos. Cosmic rays are high-energy particles that travel through space, primarily originating from sources like supernovae and black holes. When these particles reach Earth's atmosphere, they create a cascade of secondary particles that can affect technologies and pose risks for astronauts in space. For space exploration, cosmic rays represent a significant challenge. High-energy particles can penetrate spacecraft and even the human body, leading to radiation exposure. This radiation can cause cellular damage, increasing the risk of cancer and other health issues for astronauts on long missions. As a result, space agencies invest time and resources in developing shielding technology to protect both crew and equipment from these powerful particles. On the technological front, cosmic rays can disrupt electronic devices used in spacecraft and satellites. When these particles collide with the materials in circuits, they can cause glitches or even permanent damage. This is particularly concerning for critical systems, where reliability is paramount. Engineers work diligently to design systems that can tolerate or recover from such disruptions, ensuring that space missions can proceed safely and efficiently. Understanding cosmic rays is also important for future endeavors, such as missions to Mars. With longer durations in space and less protection from Earth's magnetic field, astronauts will face heightened exposure to these rays. Research is ongoing to assess and mitigate the risks to health and technology, allowing humanity to continue exploring the furthest reaches of space with confidence. Cosmic rays, the high-energy particles that originate from outer space, are studied using a variety of instruments that help scientists understand their characteristics and behavior. One primary instrument is the ground-based particle detector, which consists of large arrays of sensors placed over vast areas of land. These detectors capture secondary particles produced when cosmic rays interact with the Earth's atmosphere. By analyzing the patterns and energies of these secondary particles, scientists can infer the properties of the original cosmic rays. Another important tool is the balloon-borne detector, which is carried high into the atmosphere by large balloons. This setup allows instruments to measure cosmic rays before they collide with the atmosphere, providing a clearer view of their energy and composition. In contrast, space-based observatories equipped with special detectors orbit the Earth, avoiding atmospheric interference entirely. These instruments can directly capture cosmic rays in space, providing valuable data on their origin and the environments they come from. Neutron detectors and gamma-ray telescopes are also utilized in these investigations. Neutron detectors measure the neutrons generated from cosmic ray interactions, while gamma-ray telescopes can identify high-energy photons emitted from cosmic ray collisions with cosmic matter. Together, these instruments form a comprehensive network that helps scientists piece together the mysteries surrounding cosmic rays, their sources, and their role in the universe. Studying cosmic rays provides fascinating insights into the life cycles of stars. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from various sources, including supernovae, explosions marking the end of massive stars. When a star exhausts its nuclear fuel, it can no longer maintain its balance against gravity. This imbalance leads to its collapse, producing a tremendous explosion that releases a tremendous amount of energy and material into space, and it is during these cataclysmic events that cosmic rays are generated. By examining the nature and origin of cosmic rays, scientists can learn about the processes that occur during these stellar explosions. The particles give clues about the conditions in the environment surrounding dying stars, such as temperature, density, and the types of elements being synthesized. This information helps researchers understand nucleosynthesis, which is the process of creating new chemical elements within stars through fusion. Additionally, the study of cosmic rays informs us not only about their source events, but also about the distance these particles travel and their interactions with the interstellar medium as they journey through space. These interactions can lead to the creation of secondary particles, which can reveal more about the cosmic environment and provide a broader context of galactic evolution and the life cycle of stars. Cosmic rays serve as messengers from distant regions of the universe, illuminating aspects of stellar birth, evolution, and death. By interpreting the data they provide, Scientists keep piecing together the complex puzzle of how stars live and die, shaping the cosmos as they go along. Tracing the origins of cosmic rays is like piecing together a puzzle with many missing pieces. Cosmic rays are high-energy particles that come from space and travel at nearly the speed of light, bombarding the Earth constantly. However, their journey begins far away, often from extreme environments like supernovae or black holes, which makes determining their source quite tricky. One of the main challenges is that cosmic rays are charged particles, and as they travel through space, they interact with magnetic fields. These magnetic fields can deflect their paths, much like how a magnet affects iron filings. This means that by the time they reach Earth, their original direction is obscured, making it difficult to trace back to their point of origin. Additionally, cosmic rays vary in energy levels. Some are relatively low energy, while others are incredibly high energy, originating from the most violent and energetic events in the universe. The higher the energy, the more rare these cosmic rays are, making it harder to collect data on them. Observatories must use vast arrays of detectors spread over large areas or even underground to ensure they can capture enough information about these elusive particles. Scientists also face limitations in their technology and methods. While Earth-bound detectors can catch some cosmic rays, they cannot capture all the varieties or energies. Advanced observatories in remote locations can gather more detailed data but come with logistical challenges and high costs. Lastly, there's a lack of direct observation. Unlike other astronomical phenomena, scientists cannot simply point a telescope at a cosmic ray and see what lies beyond. Instead, they rely on indirect evidence and the analysis of secondary particles created when cosmic rays collide with the atmosphere. This requires sophisticated models and simulations to help understand where these particles might have originated. Together, these factors create a complex and dynamic field of study that challenges scientists in their quest to uncover the mysteries of cosmic rays and their sources across the universe. Cosmic rays are high-energy particles that originate from outside our solar system, traveling through space at nearly the speed of light. When these particles reach a planet, they can have significant effects on its atmosphere and potentially its evolutionary path. As cosmic rays interact with a planet's atmosphere, they can produce secondary particles, leading to a cascade of reactions that create new elements and compounds. This process can contribute to the formation of clouds and influence weather patterns. For planets like Earth, cosmic rays can also play a role in the creation of ozone in the stratosphere. Ozone is vital for blocking harmful ultraviolet radiation from the sun, which can prevent skin cancer and protect ecosystems. Additionally, cosmic rays may impact biological processes. For example, they can facilitate mutations in living organisms by interacting with DNA, introducing variations that can lead to evolution. On other planets, especially those with thinner atmospheres or weaker magnetic fields, the influence of cosmic rays can be even more pronounced. In such environments, the constant bombardment can lead to atmospheric erosion over time, potentially stripping away gases that are essential for maintaining a stable climate. This could limit a planet's ability to support life as we know it. Understanding the effects of cosmic rays allows scientists to piece together the puzzle of planetary evolution. The influence of these energetic particles demonstrates how interconnected cosmic phenomena are with the development of planets, providing a deeper insight into the processes that shape our universe. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from various sources, including supernova explosions, active galactic nuclei, and even the Sun. These energetic particles play a significant role in influencing the solar system's boundaries, specifically in the area known as the heliosphere. The heliosphere is a vast bubble created by the solar wind, which is a stream of charged particles emitted by the Sun. This wind pushes against the interstellar medium, the gas and dust that exists between stars, creating a dynamic interface. Cosmic rays interact with this solar wind and the interstellar medium, leading to complex processes that shape how the heliosphere forms and changes over time. As cosmic rays enter the heliosphere, they can ionize particles in the surrounding interstellar medium. This interaction results in changes to the density and pressure of the particles around us. We see this impact most noticeably at the heliopause, the boundary where the solar wind's influence fades and the pressure from the interstellar medium takes over. The presence of cosmic rays can help us understand the balance of forces at this edge. They might even help regulate the size and shape of the heliosphere itself. In a more intricate dance, cosmic rays contribute to the creation of secondary particles when they collide with the particles in the solar atmosphere and the interstellar medium. This cascade effect can amplify the intensity of cosmic rays within the heliosphere, influencing everything from space weather to how our planets interact with solar radiation. Thus, cosmic rays are not just random particles. They are vital players in the cosmic game, helping define the boundary between our solar system and the vast space beyond. Their interactions within this delicate balance allow us to explore and understand our place in the universe more deeply. Future cosmic ray research holds incredible potential to reshape our understanding of astrophysics. Cosmic rays are high-energy particles that travel through space, some of which originate from the most extreme environments in the universe, such as supernovae or black holes. These particles can provide insights about the energy processes occurring in these colossal events. As researchers delve deeper into this field, they can uncover the mysteries surrounding the behavior of these particles. For instance, cosmic rays can help scientists learn about the conditions necessary for matter and energy to coexist at such high energy levels. The discovery of new types of cosmic rays, or understanding their interactions with other components of the universe, can reveal the underlying physics governing astronomical phenomena. Moreover, studying cosmic rays could shed light on the makeup of dark matter and dark energy. Although these concepts are hidden from direct observation, cosmic rays might interact with them in ways that reveal their nature. By understanding how cosmic rays behave in different regions of the universe, researchers can collect valuable data that might hint at the presence and characteristics of these elusive components. Additionally, as technology advances, our capabilities to detect, track, and analyze cosmic rays will improve. Observatories and experiments designed to monitor cosmic rays across vast distances could lead to groundbreaking discoveries. Understanding the origins, spectrum, and flux of these particles can unveil the dynamics of our universe and allow scientists to refine their models of cosmic evolution. In conclusion, the future of cosmic ray research could change our entire view of astrophysics by answering fundamental questions about the universe's formation, composition, and the fundamental forces at play in its ongoing evolution. The more we understand these tiny, rapid particles, the more we may unlock the secrets of the cosmos. The search for extraterrestrial life is driven by several crucial priorities that guide researchers and space agencies around the world. First and foremost, scientists are focused on identifying potentially habitable environments beyond Earth. This means looking for planets and moons that possess the right conditions, like liquid water, essential chemicals, and a suitable temperature range, that could support life as we know it, or even forms of life that we haven't yet imagined. One significant area of interest is the study of Mars. Mars has long been a candidate for hosting microbial life due to evidence suggesting it once had flowing water on its surface. Missions like robotic rovers explore the Martian soil and atmosphere to search for signs of past or present life, such as organic molecules that are the building blocks of life. Another priority involves icy moons within our solar system, such as Europa, Ganymede, and Enceladus. These intriguing worlds are believed to have subsurface oceans beneath their ice-covered surfaces. By analyzing the plumes of water vapor expelled from these moons or planning future missions to land on them, scientists hope to uncover environments where life might thrive. Astronomers are also focused on scanning distant exoplanets, planets outside our solar system, for their atmospheres. By measuring the light that passes through a planet's atmosphere during transits, scientists can identify organic molecules or gases that suggest biological activity. Signs like the presence of oxygen or methane could be indicators of life processes. Advancements in technology and methods for detecting potentially life-supporting signals form another key priority. Programs designed to search for radio signals or other signs of advanced civilizations in our galaxy are actively pursued. Projects like the Search for Extraterrestrial Intelligence, or SETI, explore the cosmic landscape for any hints that we are not alone. In parallel, researchers focus on understanding life's potential variations, expanding the definition of what life could be. This involves studying extremophiles on Earth, organisms that thrive in extreme conditions, providing insights into how life might endure in harsh environments elsewhere in the universe. The priorities in the search for extraterrestrial life encompass identifying habitable environments, exploring Mars and icy moons, studying exoplanets, searching for signals from advanced civilizations, and broadening the understanding of what constitutes life. Together, these efforts contribute to a deeper exploration of our universe and the thrilling possibility of discovering life beyond our planet. Scientists define potentially habitable exoplanets by considering several key factors that might support life as we know it. First, they look for planets located in the habitable zone. This is a region around a star where temperatures could allow liquid water to exist on the planet's surface, which is vital for life. If a planet is too close to the star, it may be too hot, causing water to evaporate. Conversely, if it's too far away, water could freeze into ice. Next, scientists consider the planet's size and composition. An ideal candidate is often similar in size to Earth because larger planets might have crushing atmospheres and smaller ones may lack significant gravity to hold onto their atmospheres. They also analyze the planet's atmosphere, which could reveal important clues about its ability to sustain life. A thick atmosphere could support conditions necessary for weather patterns and protection from harmful radiation. Identifying these exoplanets involves using advanced telescopes and other technology to observe stars and their movements. When a planet passes in front of a star, it creates a slight dimming, which can be measured. This method, known as the transit method, helps to determine the planet's size and distance from its star. Additionally, scientists might use the radial velocity method, which measures the star's slight wobble due to gravitational pulls from orbiting planets, helping to confirm the planet's existence and provide more data about its mass. By combining all this information, location, size, atmospheric conditions, scientists can assess which exoplanets might be candidates for life. However, we must remember that finding life is an ongoing quest, and just because a planet is in the habitable zone does not guarantee it has life. It simply means the conditions are right for it to potentially exist. Astrobiology is the study of life in the universe and is essential for understanding if life exists beyond Earth. Scientists involved in astrobiology probe both the conditions that might support life and the signs that could indicate it. This scientific field explores diverse environments, from extreme conditions on Earth to the icy moons of distant planets, to understand the potential for life elsewhere. A crucial aspect of astrobiology is the search for biosignatures. These are indicators that can provide evidence for past or present life. Biosignatures can take many forms, including specific gases in a planet's atmosphere, unusual chemical patterns, or even complex organic molecules. For instance, the presence of gases like oxygen or methane in large amounts can signal biological activity, as these substances are typically produced by living organisms. When scientists look for alien life, they analyze the atmospheres of distant planets and moons for these biosignatures. Advanced telescopes can detect light from these celestial bodies and identify the chemical ingredients in their atmospheres. If they find a combination of gases that suggest biological processes, it increases the likelihood that life could be present. Additionally, astrobiologists use models to predict where life might exist based on what is known about life on Earth. They consider factors like temperature, water availability, and the presence of essential elements like carbon and nitrogen. By understanding how life thrives under various conditions, scientists can refine their search for biosignatures in the universe. Astrobiology sets the stage for humanity's quest to understand life beyond Earth, while biosignatures serve as the clues that can point to its existence. As we continue to develop technology and improve our observational capabilities, the search for these signs of life remains one of the most exciting frontiers in science. Missions like Kepler and TESS, or the Transiting Exoplanet Survey satellite, have transformed our understanding of planets beyond our solar system. Before these missions, finding exoplanets was like searching for a needle in a haystack. The methods available were limited and often based on chance observations. Kepler, launched in 2009, focused on a small patch of sky, continuously monitoring it for a long period. It employed a technique called the transit method, which watches for slight dimming of a star's light when a planet passes in front of it. This careful and repeated monitoring allowed Kepler to discover thousands of exoplanets, revealing that many stars have their own planetary systems. The data collected indicated that the universe is far more crowded with planets than we previously thought. Following in its footsteps, TESS was launched in 2018 with a broader approach. It examines nearly the entire sky over its 2-year mission. TESS is designed to identify nearby stars with orbiting planets, particularly focusing on those that are easier for researchers to follow up on with detailed observations. This mission aims to find smaller Earth-like planets in the habitable zone, where conditions might be suitable for life. Both missions have heightened our understanding of planet diversity. We now know that planets come in different sizes, compositions, and distances from their stars. This knowledge has not only expanded our catalogue of exoplanets, but has also sparked deeper questions about the potential for life on these distant worlds. With missions like Kepler and TESS, we are just scratching the surface of understanding the vast complexity of the universe's many planets. Discovering life beyond our planet would reshape our understanding of life itself, but the implications differ greatly between finding simple life forms and intelligent beings. If we find only simple life, like bacteria or microorganisms, it would suggest that the ingredients for life are common in the universe. This discovery would emphasize that life can emerge in various environments, on planets previously thought barren or hostile. It would ignite questions about the diversity of life forms and how evolutionary processes could unfold similarly, yet differently, in distant worlds. This kind of finding would encourage scientific exploration, pushing us to search for other forms of life, possibly looking for more complex organisms on moons and planets that currently harbor simple life. On the other hand, finding intelligent life would have profound consequences for humanity. Such a discovery would imply that advanced civilizations are not only possible, but perhaps more widespread than we think. It would challenge our place in the cosmos, fostering a sense of shared existence among potentially sentient beings. This revelation could lead us to reflect on our own technology, ethics, and lifestyle, prompting new conversations about cooperation and communication across the stars. With intelligent life, the potential for exchanging knowledge and culture could open doors to incredible advancements, possibly fueling our own progress in science and technology. However, it would also raise concerns about safety and the consequences of interaction with a more evolved civilization. Thus, the implications of finding life vary, shaping our understanding of the universe and our role within it in drastically different ways. The Drake equation serves as a framework for thinking about the likelihood of finding intelligent life in the universe. It was created to stimulate scientific dialogue around the question of extraterrestrial life. Imagine standing at the edge of a vast forest representing our galaxy, filled with countless trees, each one housing the potential for life to thrive. At its core, the equation includes several factors that scientists believe contribute to the probability of civilizations that can communicate. The journey begins with the rate of star formation in our galaxy, which indicates how many new stars, and potentially planets, are being born. Then, we consider the fraction of those stars that might have planets orbiting them. Given the age of our galaxy and the diverse types of stars, many likely offer these opportunities. Next, the equation factors in the number of these planets that could support life. Not every planet will be suitable. Conditions such as distance from its star and the presence of water are crucial. Following this, we look at the fraction of planets that actually develop life. Though we have only one example, Earth, scientists speculate on various pathways life could take. Once life forms, some may advance to the stage of intelligent civilizations. Here again, not all life will evolve to that level, so the equation accounts for the fraction that does. The final touch points to the lifespan of these civilizations. If a civilization can communicate, it may not last long enough for us to detect it unless conditions align perfectly. Together, these factors create an estimate of how many civilizations might exist right now capable of sending communications. It's a complex puzzle made up of several moving parts, grounded in our understanding of life and the cosmos. While this calculation involves some degree of speculation, the framework helps bridge the gap between our narrow experience on Earth and the vast possibilities within the universe. Extremophiles are remarkable organisms that thrive in some of the most hostile environments on Earth, such as deep ocean vents, boiling hot springs, and icy polar regions. Studying these resilient life forms gives scientists invaluable insights as they search for life beyond our planet. These organisms demonstrate that life can exist where we might once think it impossible, such as in extreme temperatures, high radiation, or low nutrient availability. By understanding how extremophiles adapt to these harsh conditions, researchers can expand their criteria for what defines a habitable environment. For instance, if life can thrive in the intense heat of a boiling spring or the crushing pressures of the deep sea, then it's plausible that similar life forms might exist on other celestial bodies with extreme conditions, like subsurface oceans on moons such as Europa or Enceladus. Furthermore, extremophiles also teach us about the biochemical pathways that support life in extreme settings. Some extremophiles utilize unique proteins and metabolic processes to survive, suggesting that alien life might similarly possess biochemistries we have yet to fully understand. This means that during missions to Mars or the icy crusts of distant moons, scientists may look for life forms based not solely on Earth-like conditions, but also on the diverse adaptations shown by extremophiles. Extremophiles push the boundaries of our understanding of life and inform our search for extraterrestrial existence. They remind us that life is incredibly versatile and may take forms we have yet to imagine, thriving in environments that currently seem uninhabitable. The pursuit of discovering alien life has been significantly boosted by several technological advancements. One of the most crucial developments is the construction of powerful telescopes. These instruments have the capability to see distant stars and planets in much greater detail than ever before. With higher sensitivity and resolution, they allow scientists to analyze the atmospheres of exoplanets, which are planets outside our solar system. By studying the chemical composition of these atmospheres, researchers can look for indicators of life, such as oxygen or methane, which may suggest biological processes. Additionally, advancements in space exploration technology have made it possible to send probes further into our solar system. These robotic explorers, equipped with sophisticated instruments, are designed to investigate the surfaces and atmospheres of planets and moons. For instance, missions to Mars are revealing whether the planet ever had conditions suitable for life, while missions to the icy moons of Jupiter and Saturn search for subsurface oceans that could harbor life. Artificial intelligence is also playing a vital role in the quest for extraterrestrial life. AI systems can analyze vast amounts of data collected from various sources, identifying patterns and anomalies that might suggest the presence of alien signals. These technologies help scientists sift through noise to find potential evidence of intelligent life. Furthermore, the development of nanotechnology is enhancing the sensitivity of detection tools, allowing for the exploration of biological markers at incredibly small scales. This could help in identifying simple life forms or specific biosignatures in distant environments. Lastly, the rise of collaborative global databases enables researchers from around the world to share findings and insights more efficiently. By pooling resources and knowledge, scientists increase their chances of making significant discoveries related to alien life. Together, these technological advancements create a multifaceted approach to the age-old question of whether we are alone in the universe. The possibility of extraterrestrial life introduces profound questions that can shake the foundations of both philosophical and religious beliefs. For many, the existence of life beyond Earth challenges the uniqueness of humanity. If intelligent beings exist elsewhere, it raises the question of what it means to be human and our place in the universe. Philosophically, the discovery of extraterrestrial life would demand a re-evaluation of concepts such as consciousness, morality, and existence. It could lead to new ideas about intelligence and sentience, prompting debates about whether these other beings possess similar rights or moral considerations. Would our ethical frameworks extend beyond our planet, or would we need to redefine them in light of this new knowledge? On a religious level, many faiths hold specific narratives about creation, often placing humanity at the center of the universe. The recognition of other life forms may challenge this perspective. Some might see such discoveries as a confirmation of their beliefs, interpreting them as manifestations of a divine creator's vastness. Others, however, could view it as conflicting with their sacred texts, leading to theological dilemmas about salvation, the nature of God, and the role of humanity in a broader cosmic context. Moreover, across cultures, the understanding of life and existence varies. For some, this discovery might enrich their spiritual beliefs, while for others, it could provoke fear or existential anxiety over humanity's significance. Ultimately, the search for extraterrestrial life isn't just a scientific endeavor, it's a journey into the core of our understanding of ourselves, our values, and our beliefs. This quest invites us to expand our horizons and reconsider what it means to share the universe with others. The discovery of extraterrestrial life forms could trigger profound changes across society, touching on various aspects of human existence. Imagine the excitement and wonder that would sweep the globe as people grapple with the reality of not being alone in the universe. This revelation would likely unite humanity in both curiosity and a sense of shared destiny. With an equal sense of awe and concern, many would question what it means to be human in a universe populated by other intelligent beings. On a scientific level, this find would spark an unprecedented surge in research and exploration. Scientists would endeavor to learn about these life forms, their biology, habitats, and technologies, if any exist. This could lead to new branches of study, revolutionizing our understanding of life itself. Innovations in technology and medicine might emerge as we learn from their biological systems. Culturally and religiously, various beliefs could be challenged or reinforced. Many traditions have specific teachings about humanity's place in the cosmos. The existence of extraterrestrials might lead to new interpretations of ancient texts and philosophies as people seek to understand how these beings fit into their worldviews. Economically, industries related to space exploration and technology would likely undergo significant expansion. New markets could arise, focused on communication, travel, and industries related to the study and interaction with these life forms. This might also shift how governments allocate funding for scientific endeavors, emphasizing the importance of understanding our wider universe. Finally, there would be ethical considerations. Questions would emerge about the rights of these extraterrestrial beings. How should we approach them? Would humanity be prepared to treat them with respect, especially if they possess intelligence and emotions? The answers to these questions could redefine moral frameworks and our responsibilities, not only to each other on Earth, but also to life beyond our planet. The discovery of extraterrestrial life could reshape societal structures, influencing science, culture, economy, and our fundamental ethics, ultimately challenging us to redefine our role within the cosmos. Fast radio bursts, often called FRBs, are intense flashes of radio waves that last just a fraction of a second. These bursts, which can release as much energy in that brief moment as our sun would in many years, occur over immense distances, often from galaxies billions of light-years away. Their exact origins remain a mystery, with theories suggesting they might be linked to rapidly rotating neutron stars, also known as pulsars, or even more exotic phenomena such as merging black holes. The first discovery of FRBs happened in 2007, when astronomers detected a strong pulse of radio waves that seemed to originate from outside our galaxy. Initially, these bursts puzzled scientists because they appeared sporadic and difficult to trace. However, ongoing research has led to the detection of multiple FRBs, providing a wealth of data. The study of these fast radio bursts is becoming a crucial area of astrophysics, helping researchers unlock secrets about the universe, such as the nature of cosmic matter and the behavior of extreme environments in space. Fast radio bursts, or FRBs, have captured the imagination of astronomers and physicists alike due to their mysterious nature and the challenge they pose to our understanding of the universe. These bursts are brief and powerful flashes of radio waves that originate from distant galaxies, often lasting just a few milliseconds. The sudden arrival of these intense signals can release as much energy in that short time as the sun emits in an entire day. One reason for their intrigue is the uncertainty surrounding their origin. While some FRBs have been traced back to specific galaxies, others defy identification, leading scientists to speculate about various possibilities. Are they caused by extreme astrophysical events, such as the collapse of massive stars or the merging of neutron stars? Or could they be something completely unknown, perhaps evidence of advanced technology or phenomena not yet understood? Additionally, their ability to travel vast distances raises questions about the nature of the universe and the structures within it. The way these signals are affected as they travel through space can provide insights into the intergalactic medium, the matter that fills the space between galaxies. By studying how FRBs interact with this material, scientists can learn more about the composition and density of the universe. Moreover, the sheer unpredictability of FRBs adds to their allure. They do not follow a clear pattern, often appearing randomly. This randomness presents a puzzle that astronomers are eager to solve, as it may reveal new physics or some underlying mechanism governing cosmic events. The mystery of FRBs represents a thrilling frontier in astrophysics. Each new discovery puts a piece in the puzzle of understanding the cosmos, making these bursts not just intriguing phenomena, but key to unraveling deeper cosmic mysteries. Fast radio bursts, or FRBs, are among the most intriguing phenomena in the cosmos, bursting onto the scene with powerful energy for mere milliseconds before vanishing without a trace. Their origins have sparked considerable curiosity and debate among scientists. Current theories suggest a range of possibilities, indicating a rich diversity of sources. One leading theory revolves around magnetars, which are a type of neutron star endowed with an extremely strong magnetic field. Imagine a star that has collapsed so intensely that it spins rapidly, and its magnetic field is magnified beyond anything we can conceive. When these magnetars undergo sudden magnetic shifts, they can release immense energy bursts that could manifest as FRBs. Another possibility points to the collisions of compact objects, such as neutron stars merging or even interactions between black holes and neutron stars. These cosmic events generate powerful shock waves that might create the conditions necessary for the rapid bursts of radio waves we detect as FRBs. Some researchers have also explored the idea that these bursts could come from supernova explosions, the violent deaths of massive stars. These explosions might eject material at extraordinary speeds, producing radio emissions in the process. In a more speculative realm, there is even the suggestion of technological origins, theorizing that advanced civilizations could be generating these bursts, possibly as markers or communications across vast interstellar distances. While this notion remains far from established science, it opens a fascinating dialogue about the potential for life beyond Earth. Overall, the diversity in possible sources of FRBs underscores our evolving understanding of the universe. As new radio telescopes and observational techniques come online, they may uncover more about these elusive bursts, helping us piece together the puzzle of their origins and broaden our knowledge of cosmic phenomena. Telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are changing the way we explore fast radio bursts, often called FRBs. These mysterious bursts of radio waves, lasting just a few milliseconds, have puzzled scientists since their discovery. Traditional telescopes relied heavily on manual tracking and were often limited in what they could detect. CHIME, however, is an innovative wide-field radio telescope designed to cover a vast portion of the sky simultaneously. Imagine trying to find a twinkling star in a large field with a small flashlight. It can be quite difficult. Now, picture using a massive floodlight, illuminating the entire area at once. This is how CHIME operates. It continuously monitors the sky, capturing data from many sources at the same time. This capability allows it to detect numerous FRBs that might otherwise be missed. When FRBs occur, they emit bursts of radio waves that travel billions of light years before reaching Earth. CHIME's design enables it to capture thousands of these bursts daily, greatly increasing the amount of data available for analysis. Not only can it detect the bursts, but it also helps scientists understand their origin and frequency patterns, giving clues about the environments in which they occur. For instance, analyzing the dispersion of the bursts, how they spread out over different frequencies, can hint at the density of the cosmic material they pass through. Moreover, CHIME is not just a passive viewer of these cosmic events, it plays an active role in advancing our knowledge. It can quickly determine the positions of these bursts in the sky and alert other observatories. This allows for follow-up observations using different wavelengths of light, which can unveil even more information about the objects that emitted the bursts. CHIME represents a leap forward in our ability to study fast radio bursts. By capturing an extensive range of data with its wide-field design and by facilitating a more collaborative approach to astrophysics, this telescope is helping to unravel the enigma of FRBs, one discovery at a time. Fast radio bursts, or FRBs, are mysterious bursts of radio waves that last just a few milliseconds. Their origins are still under intense study, and several hypotheses connect them to neutron stars and black holes. One intriguing idea is that some FRBs might originate from neutron stars, particularly those that are highly magnetized. These are known as magnetars. When a magnetar undergoes a violent outburst or a sudden change in its magnetic field, it could send out a burst of radio waves that we detect on Earth. Another hypothesis suggests that FRBs may be linked to black holes. In this scenario, a black hole might be involved in the merger of smaller cosmic objects. When such collisions occur, they can release massive amounts of energy, generating the intense and brief signals that we observe as FRBs. Additionally, some researchers theorized that the collapse of massive stars into black holes could produce these enigmatic bursts during specific phases of their evolution. Lastly, there are ideas that propose FRBs are connected to processes that involve both neutron stars and black holes, like interactions in binary systems. In these pairs, where one star is a dense neutron star and the other could be a black hole or another neutron star, gravitational forces might create conditions that trigger the rapid emissions we recognize as FRBs. While each hypothesis offers exciting possibilities, the exact mechanisms behind FRBs remain unclear. Ongoing research continues to explore these cosmic puzzles, aiming to unveil the true nature of these captivating phenomena. Fast radio bursts, or FRBs, are brief but intense bursts of radio waves from deep space, and classifying them has become a significant challenge for astronomers. New data handling techniques are like powerful tools that help scientists sift through the vast amounts of information collected from radio telescopes. Imagine a librarian organizing thousands of books. These techniques allow researchers to sort through countless signals, identifying patterns and distinguishing FRBs from background noise. One major advancement is the use of machine learning, a type of artificial intelligence that can learn from data and improve its accuracy over time. By training algorithms on known FRB signals, these systems can detect new bursts with remarkable precision. They recognize the unique properties of FRBs, such as their frequency patterns or duration, much faster than a human ever could. This allows astronomers to spend less time filtering through data manually and more time analyzing the properties and implications of these bursts. Additionally, the increase in computing power enables real-time processing of data streams. This means that instead of waiting days or weeks to analyze collected information, scientists can now receive insights almost instantly as the data comes in. It's like turning on a light in a dark room. You can see immediately what's there without having to fumble around in the dark. Furthermore, advancements in imaging techniques help refine how we visualize FRBs and their potential sources. By applying sophisticated algorithms, researchers can create detailed maps of the sky that highlight where these bursts are coming from and how often they appear. This enhances our understanding of their origins and could lead to discoveries about the kinds of cosmic events that create them. Together, these new data handling techniques form a robust system that not only aids in the classification of FRBs, but also paves the way for unraveling the mysteries surrounding these enigmatic signals from the universe. The more efficiently and accurately we can classify FRBs, the closer we get to understanding their nature and the powerful cosmic events that produce them. Fast radio bursts, or FRBs, are a captivating cosmic phenomenon that could unlock secrets about parts of the universe we have yet to explore. When initially discovered, these brief yet powerful bursts of radio waves puzzled scientists, leading to intense investigation into their origins. Each FRB lasts just a few milliseconds, but in that moment, it can release as much energy as the sun will emit in several years. The characteristics of FRBs tell us about the environments in which they occur. For instance, the way these bursts are scattered and the patterns of their signals can reveal clues about the materials they have traveled through, such as gas and dust. This scattering can indicate the density and composition of the surrounding medium, potentially pointing to previously undetected cosmic structures like untamed galaxies or fascinating stellar remnants. Moreover, certain FRBs appear to repeat, suggesting they might come from specific sources that can be tracked down. By identifying these sources, researchers gain insights into high-energy environments, possibly including extreme gravitational fields, magnetic activity, or even interactions in dense stellar clusters. This might hint at environments beyond our current understanding, expanding our view of what exists in the cosmos. In addition, studying FRBs could help refine our models of the universe's evolution and composition, especially regarding dark matter and dark energy. These elusive components influence the structure of the universe, yet remain poorly understood. By examining the patterns in FRBs, scientists hope to map some of these cosmic influences more precisely. Ultimately, the ongoing study of fast radio bursts serves as a gateway to exploring unexplored cosmic realms. By piecing together the information they provide, we might not only discover new cosmic environments, but also gain deeper insights into the fundamental processes shaping our universe. Fast radio bursts, often referred to as FRBs, are brief yet powerful flashes of radio waves that come from distant galaxies. These phenomena are intriguing because they contain vital information about the universe. Imagine them as cosmic beacons offering insights into the vast spaces between celestial bodies. When an FRB travels through space, it encounters various elements like gas and dust between its point of origin and Earth. Each of these elements can interact with the radio waves, changing their speed and, more significantly, their wavelength. By studying how the signals from an FRB change as they journey across the universe, scientists can glean information about the density of the material the signals pass through. This process is crucial for understanding not just the distance to the FRB itself, but also the distribution of matter in the universe. As scientists gather data from multiple FRBs, they start to build a clearer picture of cosmic structures, the web of galaxies, galaxy clusters, and the immense voids between them. These bursts can serve as markers that illuminate the cosmic landscape, revealing the intricate tapestry that makes up the universe. By comparing the frequencies and delays of these bursts from various locations, researchers can create detailed maps that show how materials are spread throughout space and how they affect cosmic expansion. FRBs act as tools to better understand the fabric of the cosmos, helping scientists uncover the complex interplay between light, matter, and space itself. As this field of study grows, the knowledge gained from FRBs will enhance our understanding of the universe's past, present, and future. To decode the signals from fast radio bursts, or FRBs, several technological innovations are essential. First, we need extremely sensitive radio receivers. These specialized devices must be able to detect faint signals from vast distances in space, where the intensity often gets lost along the way. High sensitivity allows scientists to pick up the brief, powerful bursts of radio waves, even when they are scattered over millions of light years. Next, advanced signal processing techniques are crucial. The data collected by radio telescopes is often noisy and complicated. Improved software algorithms can help sift through this data, identifying the actual signals from FRBs amid the background noise. These innovations help organize the information so that researchers can analyze it more accurately and efficiently. Additionally, real-time data analysis capabilities would greatly enhance our understanding of FRBs. By processing incoming signals as they are detected, scientists could determine the potential sources and characteristics of these bursts immediately. This would involve not just software advancements, but also more powerful computing hardware, allowing for rapid computations to handle the large volumes of data these bursts produce. Another key innovation involves the development of international collaborations and sophisticated networks of radio telescopes. By linking multiple observatories across the globe, we can improve our chances of capturing the fleeting moments of FRBs. This interconnected approach provides a clearer picture of the burst's origins and allows for more comprehensive studies. Lastly, enhancing our understanding of the ionosphere and its effects on radio signals is vital. New technologies that help model and predict how signals from space are distorted by our atmosphere will aid scientists in correcting these alterations, resulting in more accurate information about the bursts themselves. In conclusion, a combination of sensitive instruments, advanced data processing, real-time analytics, collaborative networks, and atmospheric understanding will significantly enhance our ability to decode signals from fast radio bursts, leading to groundbreaking discoveries about the universe. Fast radio bursts, often simply known as FRBs, are mysterious and powerful signals from deep space that have captivated scientists since their discovery. These brief but intense bursts of radio waves can last just a few milliseconds, making them a tantalizing enigma. As researchers work to understand their origins, they anticipate numerous future discoveries that FRBs could lead to in radio astronomy. One key area of interest is the potential use of FRBs as cosmic probes. Because their signals travel vast distances across the universe, studying how they interact with matter along their path can reveal essential information about the universe's structure. For instance, observing changes in the properties of FRBs can provide insights into the distribution of dark matter, the unseen substance that makes up much of the universe's mass. This could enhance our understanding of cosmology, the study of the universe's origins and evolution. Additionally, FRBs could help refine our knowledge of neutron stars, the incredibly dense remnants left after supernova explosions. Many FRBs appear to originate from areas with neutron stars, and detailed study might shed light on their magnetic fields and internal structures. This research could also lead to new discoveries about the behavior of matter under extreme conditions, such as those found in neutron stars, which are unlike anything we encounter on Earth. Moreover, FRBs are becoming valuable tools for studying the intergalactic medium, the matter that exists between galaxies. By measuring the dispersion, the delay caused by different frequencies traveling at different speeds of FRB signals, scientists can learn about the density and composition of the material that surrounds them. This information helps paint a clearer picture of how galaxies evolve and interact over time. In the future, as detection technologies improve, scientists expect to discover more repeating FRBs, allowing for a deeper analysis of their behavior. Repeating signals could hint at specific mechanisms or environments responsible for their emission, further unraveling their mysteries. Fast radio bursts hold the potential to revolutionize our understanding of the universe, from the nature of dark matter to the properties of neutron stars and beyond. Each new discovery connected to FRBs may open additional avenues of research, making them a key focus in the field of radio astronomy for years to come. Tabby's star, also known as KIC 8462852, is a fascinating star located about 1,500 light-years away from Earth in the constellation Cygnus. Its allure comes from its unusual light fluctuations, which have puzzled astronomers since they were first observed. Unlike typical stars, which dim and brighten in a regular pattern due to orbiting planets or other celestial phenomena, Tabby's star exhibits mysterious and dramatic dips in brightness that seem irregular and unpredictable. This star grabbed significant scientific attention when observations indicated that it could lose over 20% of its light for days or even weeks at a time. Such extreme changes are rare and suggest that something extraordinary is happening around the star. Several hypotheses have been proposed to explain these variations. One possibility points to the presence of a swarm of comet fragments or debris orbiting the star, which might cause the light to dim as these bodies pass between us and the star. Another, more speculative idea is that the star could be surrounded by an artificial structure built by an advanced extraterrestrial civilization, a notion that stirred imaginations and sparked widespread interest among both scientists and the general public. While this theory remains a long shot, it highlights the intrigue surrounding Tabby's star and the continued search for signs of alien life. As astronomers continue to study this enigmatic star with more advanced technology and methods, they hope to unravel its secrets, learn more about the environments of other stars, and perhaps even gain insights into the possibilities of life beyond our own planet. Tabby's star, a mysterious and captivating celestial body, has captured the attention of astronomers and stargazers alike due to its strange dimming patterns. Unlike most stars that shine steadily, Tabby's star has shown significant and irregular dimming, with some events causing it to lose brightness by more than 20%. This peculiar behavior puzzled scientists, leading to various hypotheses. One of the most striking observations is the star's sporadic dimming over periods ranging from days to years. The fluctuations do not follow any regular cycle, making it difficult to predict when the next dimming will occur. Some researchers initially speculated that this could be the result of a massive swarm of comets obscuring the star's light, but the extent and inconsistency of the dimming suggested something more complex might be at play. Another intriguing idea considered by scientists is the possibility of large artificial structures orbiting the star. This notion, while exciting, is more speculative and arises from the star's behavior resembling what we might expect if a civilization were constructing colossal megastructures to capture energy. While no direct evidence supports this, it ignites the imagination about the potential for advanced life forms existing beyond our solar system. Skeptics have pointed out that natural phenomena could explain the star's behavior, including dust clouds or unique material that might block the light in unexpected ways. Studies continue, with astronomers utilizing various telescopes and observational techniques to understand the underlying mechanisms causing the unusual brightness changes. Ultimately, Tabby's star remains a symbol of the mysteries that lie within our universe, showcasing not only the limits of our current understanding, but also the endless questions that drive our exploration of the cosmos. Tabby's star, officially known as KIC 824-691, has captured the curiosity of astronomers and the public alike due to its unusual light patterns. The star exhibits significant and irregular dimming, which stands out from what we typically observe in other stars. This has led to a variety of explanations, both natural and artificial. On the natural side, some scientists propose that the dimming might be caused by clouds of dust or debris. Imagine a light bulb shining through a window obscured by layers of pollen or smoke. These particles would temporarily block the light, causing it to appear to fade. Similarly, dust orbiting around Tabby's star could obscure its brightness when viewed from Earth. Another possibility is that there could be a large number of comets, perhaps more than is typical, passing in front of the star. If they were to cluster together in their orbit, they could cause spikes in the dimming effect, lending to the star's erratic brightness. On the other hand, the more speculative explanations touch on the possibility of artificial structures. Some have suggested that the unusual behavior could indicate the presence of an enormous megastructure built by an advanced civilization, designed perhaps to harvest energy from the star. This concept captures the imagination, as it implies a level of technological advancement beyond our current understanding. Such a construction, akin to a massive solar panel system, might be observed as the star's light fluctuates when these structures pass in front of it. Ultimately, the ongoing research seeks to gather more data to determine which explanations are more likely. Each theory highlights how our understanding of the universe can vary dramatically, ranging from natural phenomena we can closely study to the tantalizing idea that we might not be alone in the cosmos. Through continued observation and technological advancements, we hope to unpack the mystery surrounding Tabby's star and uncover what truly lies behind its enigmatic dimming. Citizen science has played a remarkable role in the investigation of Tabby's star, a star that has intrigued both scientists and the public alike due to its unusual dimming patterns. The journey began when a group of amateur astronomers, working together on a project called Planet Hunters, discovered significant variations in the brightness of Tabby's star. This was not an ordinary occurrence and sparked widespread curiosity. These citizen scientists analyzed data collected from space telescopes, particularly data from a mission designed to search for exoplanets. By combing through images and brightness measurements, they identified that Tabby's star dims in ways that could not be explained by standard astronomical phenomena, such as planets passing in front of it or natural stellar activity. Instead, it showed deep and irregular dips in brightness, which led to numerous theories about what could be causing these changes. The involvement of citizen scientists extended beyond just data analysis. They provided fresh perspectives and creative ideas that professional astronomers often miss in their routine work. Their collective efforts fostered a collaborative spirit, enabling researchers to focus on formulating hypotheses and conducting follow-up studies. This combination of professional and amateur expertise brought invaluable attention to the star, leading to more extensive observations using large telescopes. In conclusion, citizen science has transformed the investigation of Tabby's star from a scientific curiosity into a global phenomenon, engaging a community of enthusiasts in the search for answers about one of the universe's most puzzling stars. Their contributions have not only enriched the scientific dialogue, but have also demonstrated how collaborative efforts between professionals and amateurs can uncover the mysteries of the cosmos. Astronomers have a fascinating mystery to unravel when it comes to Tabby's star, officially known as KIC 8028. This star has been observed to dim dramatically and unexpectedly at irregular intervals. To understand what might be causing this unusual behavior, Scientists first look to conventional explanations before considering more exotic possibilities. One common reason for a star's dimming is a planet passing in front of it, also known as a transit. This is a standard method of observation in astronomy. However, in the case of Tabby's star, the drops in brightness are far too large to be attributed to a single planet. These dips can reach more than 20%, much greater than what a planet could mask. Astronomers have also analyzed the light patterns and found no consistent, repeated dips that would suggest a typical planetary presence. Another potential explanation involves clouds of dust or debris obscuring the star's light. This is a plausible scenario because dust can scatter and absorb light. Yet studies show that any dust would need to be extraordinarily dense and located in a very specific arrangement to account for the peculiar and varying levels of dimming observed. Such a scenario becomes less convincing when considering the star's behavior over time. Speculation about artificial structures has also been considered, particularly a Dyson sphere, a hypothetical megastructure built around a star to capture its energy. However, this theory hasn't gained substantial support among scientists because it lacks evidence. No signs or emissions typical of such structures have been detected. To further rule out conventional explanations, astronomers utilize sophisticated data from multiple telescopes and observatories. By analyzing light spectra, they can look for signatures that would indicate the presence of planets or dust. They have even engaged in ongoing monitoring of the star to catch and study its behavior during dimming events more precisely. Each of these methods has helped narrow down possibilities, highlighting the need for meticulous investigation. Despite the traditional explanations being ruled out, Tabby's star still poses a tantalizing mystery, inviting researchers to explore deeper and consider even more extraordinary ideas about its elusive behavior. Imagining an artificial structure around Tabby's star opens a fascinating window into advanced technology and civilization. Tabby's star, also known as KIC 800-780, has intrigued scientists due to its unusual dimming patterns that suggest something is blocking its light in ways we do not fully understand. If a civilization were to construct a large structure around this star, one concept could be the creation of a Dyson sphere. A Dyson sphere is a theoretical concept where an advanced civilization harnesses the energy output of a star on a grand scale. This could mean building a vast collection of solar panels or habitats surrounding the star to capture its energy. The implications of such a structure would be profound. First, it would provide a nearly limitless energy source for that civilization, allowing for technology and expansion far beyond our current capabilities. Such a megastructure would also change the dynamics of the star system itself. The mass and light output would be impacted, potentially leading to temperature changes within any nearby planetary systems. This might influence the habitability of those planets, turning them into appealing environments, or making them entirely uninhabitable. Additionally, the construction of an artificial structure around Tabby's star would suggest that intelligent life forms possess technology and resources far beyond our imagination. Discovering evidence of such a structure raises questions about communication with extraterrestrial civilizations and could potentially shift our understanding of life in the universe. Exploring such a monumental feat invites further inquiry into how such civilizations manage challenges such as resource allocation, structural integrity, and the social implications of living in a stellar environment. Ultimately, if a structure were found around Tabby's star, it would not just redefine our view of that specific star, but also spark a new perspective on the potential of life beyond Earth. Tabby's star has captivated scientists and the public alike due to its unusual light patterns that don't match what we expect from a typical star. By continuing to monitor this star, we stand to deepen our understanding of various stellar phenomena significantly. Each time the star dims or brightens, it hints at unique processes occurring in its surroundings. First, consistent observation allows researchers to track these flickering changes over time. Imagine being able to see how a star behaves like a mysterious person. Over time, patterns may emerge, revealing whether these shifts are periodic or random. Recognizing a pattern can guide scientists in determining if they are witnessing a phenomenon like a cloud of dust passing in front of the star or something more exotic, such as the presence of a large object, which could be a planetary body or remnants of a shattered comet. The star's unusual dimming could also ignite discussions about stellar evolution, which is how stars change over their lifetimes. If we can gather enough data, we might learn more about how stars like Tabby's star behave as they age, or how they interact with neighboring celestial bodies. Each piece of data we gather adds to our arsenal of knowledge, potentially reshaping existing theories surrounding star behavior. Moreover, this ongoing observation contributes to our understanding of habitable zones around stars. If we can confirm that planets exist around Tabby's star, we may learn about their atmospheres, climates, and even signs of life. Understanding other stars' behaviors could refine our models for searching for life beyond Earth, allowing us to adjust our expectations and technologies accordingly. Continued scrutiny of Tabby's star acts like a magnifying glass on the universe's mysteries. With each new observation, we gather insight that could reframe our grasp of stellar life cycles and the complex interactions that occur within galaxies. This small but mysterious star challenges our assumptions, and in doing so, pushes the boundaries of our cosmic knowledge forward. To comprehend enigmatic stars like Tabby's star, scientists need advancements in various areas of technology and astronomy. One significant area is the improvement of observational tools, particularly more powerful telescopes equipped with high-resolution capabilities. These tools would allow astronomers to gather clearer and more detailed images of these mysterious stars, facilitating the study of their light patterns and any potential irregularities. In addition, advancements in spectroscopy, the study of the interaction between light and matter, are crucial. Enhanced spectroscopic techniques can help scientists analyze the composition of a star's light, revealing essential information about its atmosphere and behavior. This can lead to a better understanding of why some stars exhibit unusual dimming or flickering. Another important technological improvement involves data analysis. As scientists gather vast amounts of information from observations, strong computational methods and machine learning algorithms can process and interpret this data more efficiently. This would enable researchers to detect patterns and anomalies that might otherwise go unnoticed. Lastly, collaboration with space-based observatories is vital. Developing smaller, cost-effective satellites to complement existing space telescopes would allow for continuous monitoring of these stars. This is important because changes in their brightness can happen over time, and ongoing observations can yield valuable insights. A combination of enhanced telescopes, improved analysis techniques, and continuous monitoring capabilities will pave the way to unlocking the mysteries of enigmatic stars like Tabby's star. The goal is to turn uncertainties into understanding, revealing more about the universe and the stellar phenomena that challenge our current knowledge. Scientists are curious about Tabby's star because of its unusual pattern of dimming. This star experiences dips in brightness that are unlike what is seen with typical stars. To understand these strange occurrences, researchers are conducting a series of observations and experiments. First, astronomers use powerful telescopes to monitor Tabby's star over time. They collect light data to see exactly how the brightness changes. By studying this light more closely, they aim to determine if the dimming is due to something like a cloud of dust or a group of comets passing in front of the star. Light from the star interacts differently with various materials, so analyzing these changes provides clues about what might be causing the dimming. Another approach involves comparing Tabby's star to other stars with similar characteristics, but without the dimming. These comparisons help scientists establish what is normal for such stars and identify any outliers like Tabby's. Learning more about typical behaviors allows researchers to pinpoint how Tabby's star strays from the norm. Additionally, scientists are keen to use data from different wavelengths of light. Stars can emit energy not just in visible light but also in infrared, radio waves, and other kinds of radiation. Observing Tabby's star in these different wavelengths can reveal more about its environment and whether something unusual is affecting its brightness. Lastly, they can conduct theoretical modeling, which involves creating simulations to replicate the conditions around the star. By testing these models against the observed data, scientists can explore various scenarios and see which fits the dimming behavior best. Through these combined efforts, monitoring, comparing, analyzing different types of light, and developing simulations, researchers hope to solve the mystery behind Tabby's star's puzzling dimming and determine whether it's a natural phenomenon or something even more intriguing. Tabby's star, also known as KIC 88025, has puzzled astronomers since its unusual light fluctuations were first observed. The star dims in ways that do not neatly fit into any existing astronomical models. It swells and fades unexpectedly, suggesting that something unusual is blocking its light. One of the most exciting yet perplexing theories proposed is that a vast structure may be surrounding the star, such as a swarm of comets or even a megastructure built by an advanced civilization. While each explanation has merits, none completely explains all the observed behaviors. This ongoing mystery highlights the limits of our astronomical knowledge. Many phenomena in the universe remain unpredictable or misunderstood. Studying Tabby's star reminds us that our techniques and theories in astronomy have limitations. As we observe the cosmos, we can only interpret the data with the tools we currently possess. Mysterious objects can stretch our understanding and show gaps in our knowledge about stellar evolution, cosmic dust, and the potential for extraterrestrial life. Tabby's star serves as a powerful reminder of the universe's complexity. It encourages scientists to keep pushing the boundaries of discovery, continually refining theories and instruments to capture the many wondrous secrets that escape our current understanding. The enigma of this star fuels curiosity and highlights that the universe still holds many surprises, urging us to embrace scientific exploration with an open mind. The Voyager space probes, Voyager 1 and Voyager 2, were launched in the late 70s with groundbreaking goals. The primary mission was to explore the outer planets of our solar system, specifically Jupiter and Saturn. Scientists aimed to gather detailed data on these giant planets, including their atmospheres, magnetic fields, and moons. The missions expanded to include detailed studies of the rings surrounding these planets, which had remained largely mysterious. Each probe was designed to capitalize on a rare alignment of the outer planets, which allowed for a gravitational assist, essentially using the planet's motion to increase speed and adjust direction without using extra fuel. As Voyager 2 continued its journey, its mission was extended to include Uranus and Neptune, offering a rare glimpse into those distant worlds. The probes also aimed to gather information about the heliosphere, the vast bubble of solar wind that envelops our solar system, and to eventually enter interstellar space to study the environment beyond the influence of our sun. In time, these ambitious goals grew to include messages aimed at possible extraterrestrial civilizations, ensuring that our planet's existence was known should any intelligent life ever encounter the probes. Voyager's journey represents not just a quest for knowledge, but also an effort to connect humanity with the broader cosmos. Voyager 1 and Voyager 2 have fundamentally changed our view of the solar system. Launched in the late 70s, these spacecraft were designed to explore the outer planets, but their discoveries reached far beyond that. As they journeyed through space, they provided unprecedented close-up images and invaluable data about the gas giants, Jupiter, Saturn, Uranus, and Neptune. Voyager 1's stunning photographs of Jupiter revealed its swirling storms and the intricate details of its rings and moons. It offered a striking look at the Great Red Spot, a colossal storm that has been raging for centuries, and showcased how dynamic and complex this gas giant truly is. Voyager 1 continued its voyage beyond the planets, crossing into what we call interstellar space, the area between stars filled with sparse gas and cosmic particles. It sent back data indicating that the environment here is incredibly different from what we experience in the inner solar system. Voyager 2, meanwhile, was the first and only spacecraft to provide close-up observations of Uranus and Neptune. It helped us understand Uranus's peculiar tilt, making it an oddball among planets, and unveiled Neptune's vibrant blue color and shifting weather patterns. The findings from both Voyagers changed our understanding of planetary formation and atmospheres, highlighting the dynamic activities and mysteries of the outer solar system. Moreover, the missions helped define the boundaries of our solar system. Voyager 1's entry into interstellar space demonstrated how solar wind, the stream of charged particles from the sun, interacts with the surrounding interstellar medium. The data collected have contributed to our understanding of magnetic fields, cosmic rays, and the effects of radiation beyond our solar neighborhood. In addition to their scientific contributions, the Voyagers carry a golden record, a time capsule intended to communicate the story of our world to potential extraterrestrial life. This adds a philosophical dimension to their missions, symbolizing humanity's desire to connect with the universe. Voyager 1 and Voyager 2 have expanded our understanding of the solar system through detailed exploration, revealing the wonders of distant worlds, defining the edges of our solar system, and continuing to send knowledge back to Earth, a testament to human ingenuity and curiosity. The Voyager probes have transformed our understanding of the solar system since their launch in the late 1970s. As they journeyed beyond the reaches of our planet, these spacecraft sent back astonishing discoveries that have provided significant insights into our celestial neighborhood. One of the key findings came from Voyager's encounters with the outer planets. Voyager 1 revealed the intricate details of Jupiter's atmosphere, including its Great Red Spot, a massive storm bigger than Earth, and the discovery of intricate cloud patterns. The probe also uncovered dozens of previously unknown moons, including the largest of Jupiter's moons, known as Ganymede, which is notable for its potential subsurface ocean. Voyager 2 followed closely behind, providing detailed observations of Saturn. This probe unveiled the complex structure of the planet's rings and identified a multitude of fascinating moons, such as Titan, which is shrouded in a thick atmosphere and has the presence of liquid methane lakes on its surface. This discovery opened up new discussions about the potential for life in environments very different from our own. As both Voyagers continued their journey, they reached the outer edges of the solar system. Voyager 1 became the first human-made object to enter interstellar space, where it found a surprising amount of cosmic rays and confirmed that the environment beyond our solar bubble is unlike anything within it. This marked a historic milestone, as it offered a glimpse into the vast expanses that lie beyond our solar system. One of the most significant moments came when Voyager 2 visited Uranus and Neptune. It was the only spacecraft to ever fly past these ice giants. Voyager 2 revealed Uranus's unique tilt and complex ring system, while providing stunning images and data about Neptune's striking blue color and powerful storms. The Voyager missions also carried a golden record, a time capsule of sorts, that contains sounds and images representing the diversity of life and culture on Earth. This record serves not only as a message to any potential extraterrestrial civilizations, but also as a reminder of humanity's place in the universe. The Voyager probes have not only expanded our knowledge of the planets and their moons, but have also pushed the boundaries of exploration, providing humanity with remarkable insights into our solar system and beyond. Their missions have stitched together a narrative of our cosmic neighborhood, revealing the complexity and beauty that exists just outside our doorstep. The golden records aboard the Voyager probes are unique time capsules meant to communicate with potential extraterrestrial intelligence. Imagine sending a message across the vast emptiness of space, hoping it reaches a distant civilization. The records contain sounds and images that capture the essence of life on Earth. This includes greetings in multiple languages, musical pieces from various cultures, and images depicting everything from our planet's landscapes to human activities. Each aspect of the record was chosen carefully to convey a sense of who we are as a species. The sounds range from the laughter of children to the calls of birds, showcasing the rich tapestry of life that exists on Earth. The music includes genres spanning classical to traditional, illustrating our emotional expressions and cultural diversity. Visual images play a crucial role as well. They offer a glimpse into our world, including pictures of people, animals, plants, and significant achievements like our architecture and science. This visual storytelling is intended to provide an understanding of human existence, our environment, and the universe we inhabit. The design of the golden records also considers the possibility of extraterrestrial beings encountering them. They are constructed to withstand the harsh conditions of space, and instructions are included on how to play the records, though it is uncertain if the recipients would comprehend them. The golden records reflect our hopes for connectivity, understanding, and peace, serving as a beacon of humanity's desire to reach out beyond our planet and share our story with whoever might be out there. The Voyager spacecraft have embarked on an extraordinary journey, pushing the boundaries of human exploration beyond our solar system. As they venture into interstellar space, they encounter several significant challenges. One primary concern is the vast distance and the isolation that space presents. Although both Voyagers are traveling through empty space, they encounter cosmic rays, which are energetic particles generated by various cosmic events. These rays pose a threat to the spacecraft's instruments and electronics, potentially causing malfunctions or degradation over time. Another challenge is the extreme cold of space. As the Voyagers travel farther from the Sun, they face a drop in temperature that could severely affect their systems. To combat this, the spacecraft are equipped with power sources like radioisotope thermoelectric generators. These generators convert heat from radioactive decay into electricity, allowing the instruments to function in the freezing environment. However, as time progresses, the amount of usable power decreases, which means that scientists have to manage power usage carefully to ensure that critical systems remain operational. Communication is also a significant hurdle. As the distance between the Voyagers and Earth increases, transmitting signals takes longer. What would once be a quick conversation can now take hours for messages to travel one way, leading to significant delays in commands and data retrieval. Moreover, the attenuation of signals over vast distances means that the spacecraft's weak signals can be easily lost, making reliable communication difficult. Additionally, unexpected events in space, such as micrometeoroid impacts, can jeopardize their journey. Although the vastness of space means these events are infrequent, any collision could potentially damage critical parts of the spacecraft. The Voyagers are constructed with durable materials, but they are not invulnerable. Despite these hurdles, the Voyager missions continue to provide invaluable information about our universe, reminding us of the determination and ingenuity of human exploration. Their journey teaches us about resilience in the face of adversity and the unyielding spirit of discovery that drives us to understand our place in the cosmos. The Voyager spacecraft, launched over 40 years ago, have provided invaluable data that deepens our understanding of the heliosphere. The heliosphere is like a bubble surrounding our solar system, created by the solar wind, streams of charged particles emitted by the sun. This protective bubble extends far beyond the planets, shielding us from cosmic radiation. As the Voyager probes traveled further and further from Earth, they crossed the boundary where the solar wind's influence wanes, which scientists refer to as the heliopause. This point marks the edge of the heliosphere and the beginning of interstellar space, where the environment is shaped by the material from other stars. Voyager data has shown us how the solar wind interacts with the interstellar medium, the material between stars. The spacecraft detected variations in cosmic rays, those high-energy particles that travel through space, and measured changes in magnetic fields. This information helps scientists better grasp the structure and dynamics of the heliosphere and how it acts as a shield against more dangerous particles. Furthermore, the Voyagers have also provided insights into how the heliosphere changes over time, especially as the Sun goes through its solar cycle, which lasts about 11 years. This cycle influences the intensity of solar wind and cosmic rays reaching our planet. By studying the data collected by the Voyager probes, researchers can now more accurately model and predict the behavior of the heliosphere and, in turn, safeguard our technology and ecosystems that depend on the balance it provides. The journey of the Voyager spacecraft has transformed our understanding of the solar environment, illustrating how the heliosphere serves as our first line of defense in the vastness of space. The Voyager missions, launched in the late 70s, marked a pivotal moment in our quest to explore the cosmos. These spacecraft were engineered to journey beyond the known boundaries of our solar system, and they have left a profound legacy that continues to influence space exploration today. One of the most significant contributions of Voyager is the wealth of data it collected and sent back. As it passed the giant planets, Voyager provided breathtaking images and important scientific observations that reshaped our understanding of these worlds. The findings from Voyager have informed future missions and guided the scientific community in refining their approaches to studying distant planets. The Voyager missions also brought the idea of interstellar exploration into the limelight. By reaching the outer planets and continuing onward towards the edges of the solar system, they demonstrated the feasibility of sending spacecraft to areas previously deemed unreachable. This achievement has inspired subsequent missions aimed at exploring far-off celestial bodies, such as comets and asteroids, and has kindled interest in missions designed to study the heliosphere, the vast bubble of space dominated by the solar wind. Another legacy is the famous Golden Record carried aboard each spacecraft. This disc contains sounds and images meant to represent the diversity of life and culture on Earth. Intended as a message to potential extraterrestrial life, it symbolizes humanity's desire to connect beyond our planet, reinforcing the spirit of exploration and curiosity. This thoughtful inclusion has sparked conversations about communication with other civilizations and the fundamental questions of existence beyond our own world. Moreover, Voyager's journey has laid the groundwork for advancements in technology and engineering. The challenges of operating spacecraft over such vast distances, requiring them to function reliably for decades, have led to innovations that benefit various fields, from telecommunications to materials science. Finally, the Voyager missions have encouraged a sense of unity and curiosity among humanity. By showing us distant worlds and what lies beyond our solar system, they remind us of our shared existence on a small blue planet in a vast universe. This perspective is critical as we look toward future explorations, including potential manned missions to other planets and beyond. The legacy of the Voyager missions goes beyond data and technology. It encapsulates the very essence of exploration, an enduring quest for knowledge that continues to inspire future generations in their journey through the stars. The Voyager spacecraft have been traveling through space for over 40 years, and their continuous operation has had a profound impact on scientific research. These spacecraft carry an array of scientific instruments designed to gather data about our solar system and beyond. As they venture farther from Earth, they collect information on cosmic rays, magnetic fields, and the composition of interstellar space, contributing to a deeper understanding of the universe. The data transmitted back by the Voyager instruments allows scientists to study phenomena that cannot be observed from Earth. For instance, as Voyager 1 crosses the boundary into interstellar space, it provides insights into the characteristics of this region, revealing information about solar wind and the environment beyond our solar system. This knowledge helps researchers understand not only the immediate cosmic neighborhood, but also informs theories about the structure and behavior of galaxies. Moreover, the long-term operation of these instruments is crucial for tracking changes in space over time. Each day, Voyager gathers data on the fluctuating conditions in space, creating a continuous record that enhances our understanding of space weather and the dynamics of our solar system. This ongoing research can lead to discoveries about how solar events impact Earth and the broader solar system. Finally, the technological achievements of Voyager's instruments inspire current and future missions. Researchers refine and innovate based on the successes and challenges faced by these spacecraft. The legacy of Voyager extends far beyond its initial mission, driving exploration and encouraging new generations of scientists to ask questions about the universe and pursue groundbreaking answers. Thus, the continuous operation of the Voyager instruments not only enriches our current scientific knowledge, but also lays the groundwork for future explorations of the cosmos. The Voyager missions serve as a remarkable case study for long-term space exploration. Launched in the late 70s, these spacecraft were designed for a 5-year mission to explore the outer planets. However, they continue to transmit data more than 4 decades later, showcasing the importance of robust engineering and thoughtful design in space travel. One key lesson from Voyager is the necessity of building durable and self-sufficient systems. These spacecraft were constructed to withstand the harsh conditions of space, including extreme temperatures and radiation. Their instruments were made to be resilient yet versatile, allowing them to gather data from diverse environments even after many years. This emphasizes the importance of planning for longevity in mission design. Another significant aspect is the value of redundancy. Voyager carries multiple instruments to perform similar tasks. If one fails, others can still function. This redundancy increases the chances of continued scientific success throughout the mission's life cycle, suggesting that future missions should prioritize similar strategies to mitigate the risks of equipment failure. The Voyager missions also teach crucial lessons about the importance of communication. Despite their great distance, these spacecraft send valuable data back to Earth using a limited bandwidth. Engineers learn to compress large amounts of information and transmit it efficiently, a practice that can inform future missions as distances and challenges grow. Additionally, the Voyager spacecraft have sparked a sense of curiosity and connection. Their famous pale blue dot photograph, which depicts Earth from an unimaginable distance, reminds us of our place in the universe. This illustrates the power of exploration to inspire and educate humanity, emphasizing not only the scientific but also the philosophical importance of space missions. Ultimately, the Voyager missions highlight that successful long-term space exploration requires durable design, strategic redundancy, efficient communication, and an ability to inspire beyond the scientific realms. These components resonate as guiding principles for future endeavors into the uncharted cosmos. The Voyager missions represent a groundbreaking chapter in human exploration, acting as our ambassadors to the cosmos. Launched in the late 70s, these spacecraft journeyed beyond our immediate celestial neighborhood, sending back mesmerizing images and invaluable data about the outer planets and their moons. Their success inspires an entire generation of future explorers and scientists. Imagine a curious child looking at pictures of Jupiter's swirling clouds or Saturn's magnificent rings for the first time. These stunning visuals captivate young minds, igniting a passion for space and a desire to understand the universe. The stories of Voyager highlight the excitement of discovery and the possibility of venturing into the unknown. They demonstrate that with innovation, determination, and a bit of creativity, we can reach farther than we ever thought possible. Additionally, the scientific discoveries made by Voyager have reshaped our understanding of the solar system. Learning about phenomena like the intense magnetic fields of Jupiter or the geysers of water vapor on Enceladus makes the study of planets not just a subject in school, but a thrilling adventure. Engaging lessons rooted in real-world discoveries foster a sense of wonder and challenge students to think critically about the universe. Moreover, Voyager's ongoing journey into interstellar space teaches the next generation about perseverance. These missions were launched decades ago, yet they continue to communicate with Earth, traveling farther than any human-made object in history. This longevity is a testament to human endeavor, suggesting that when we set bold goals, we can achieve remarkable things that last generations. Finally, touching on the broader implications of the Voyager missions, their golden record sends a message to any intelligent life that might intercept it, offering a glimpse into humanity. This idea encourages young dreamers to consider their role in the universe and inspires questions about existence, possibility, and our place within the cosmos. The Voyager missions are not just about exploring the outer planets. They are a source of motivation, creativity, and hope for a new generation of explorers and thinkers. Their legacy continues to resonate, encouraging youth to look up at the night sky and dream of what lies beyond.